pour cette session du séminaire Bourbaki. Et aujourd'hui, on a pour notre premier exposé le plaisir d'accueillir Alexandros Eskenazis, qui va nous parler de tout ça, direct distortion, unbounded, nonlinear spectral gaps, and a metric Jones theorem.
Okay, thanks a lot. Can everybody hear me? Good. Great, thanks a lot, Olivier. Many thanks for the invitation. It's, of course, a great pleasure to speak at the Bourbaki seminar, and even more so to speak about this wonderful work of Nauer. So let me just start with the maths. Now, this is a talk about finite dimensional norm spaces. So the main object that we will be studying is a finite dimensional norm, meaning that we have Rd equipped with an arbitrary norm. These are, of course, the axioms of norm that you all know. So it's a positively homogeneous function that's zero only at zero and satisfies the triangular inequality. Now, this is an analytic object. And as probably again all of you know, it has a geometric counterpart, and we are going to be thinking about those two interchangeably. The geometric counterpart is given by the following correspondence, saying that finite dimensional norm spaces correspond to origin symmetric compact convex sets in R to the power d with non-empty interior. And what is the correspondence? Well, if you have a norm in Rd, then you can map it into the compact convex set, which is it's a closed unit ball. Okay, you can take that this is indeed a symmetric convex set. And the inverse of this map, if I give you a convex set K like this, then the gauge, the norm which defines this convex set, so the norm of vector x is the minimum multiple of convex set such that x belongs in this multiple. Okay, and then you can check this is a norm, and this is indeed a one-to-one correspondence. And you know, from the point of view of infinite dimensional function analysis, these spaces are always isomorphic just when you fix the dimension. So one could say that, well, the structure is reasonably simple, but this just means that one has to look for more subtle geometric properties, and you see that there is a great somehow richness of geometries here. So you see, just for to elaborate, so you know, to the left we have a high-dimensional cube, which is the unit ball of the L infinity norm. Under it we have a parallelepiped, which is just a linear image of a cube. And in the middle, of course, we have the round ball in Rd, which is the unit ball of the classical Euclidean metric. So it's the one which comes from a Hilbertian structure, and the ellipsoid, which is a linear image of that. But of course, there are much more complicated space. For instance, there we have the octahedron, which is the unit ball of the L1 norm, or the dodecahedron, which is a unit ball of some other more complicated norm. Okay, so there's quite a variety of space in this class. And if we want to understand it, we would at the very least want to ask ourselves how big is the class. And one way to measure some bigness would be to say choose a representative, which you think you understand, and then how far is everything else from this representative in a reasonable distance. Now the reasonable distance in this class is actually the Banach-Mazur distance. It's the distance between norm spaces. And the answer, and the obvious representative is of course Hilbert space, is of course the round ball in the family of convex sets. So the answer to this question, how far is a general d-dimensional norm from being Hilbertian, is answered by a famous theorem of Fritz-Zahn from 1948, which says in analytic terms that for any d-dimensional norm space, no matter what the norm is, there exists a linear map mapping it into the standard Euclidean space, which I'm going to denote by L2 of dimension d, such that the operator norm of t times the operator norm of its inverse is bound above the square root of d. Now, operator norm of t times operator norm of t inverse is a measure, it's something which measures how far you are from being a rescale on the isometry. Okay, so if this is equal to 1, you're just a rescaling of an isometry. So up to rescaling your map, this means the Euclidean norm of Tx is bound below by the norm of x, the arbitrary norm, and above by square root of d times the arbitrary norm of x. So we basically squeeze a Euclidean norm within a square root of d factor of the initial norm. And this is an analytic statement, but I told you that there is a geometric reformulation of all those things, and the reformulation is the following very simple statement. Take any compact symmetric convex set in Rd, then I can find an ellipsoid such that the ellipsoid is contained in my convex set, and the convex set is contained in square root of d times the ellipsoid. And of course, you see that the factor that you have to scale, John tells you that it's square root of d, but of course you can imagine situations where it's actually substantially less. So to the left we have a parallelogram in which you actually need the square root of 2 in this case. On the right hand side we have a linear image of an octagon which looks more like a circle or more like an ellipsoid in this case, and therefore you need a smaller factor. And what I just said is also provable. So the factor square root of d in general cannot be improved. And one example for this is the cube. Okay, so there is no way to put an ellipsoid inside the cube such that if you want to scale it so it contains the cube, the factor is smaller than square root of d. So the supremum norm is extremum with respect to the statement. And square root of d absolutely sharp. If there are any questions, by the way, please interrupt me. So this completely settles the distance from a Euclidean space. I should say that if one were to choose a different representative from the class of d-dimensional norms rather than Euclidean space, then automatically you bump into major open problems that are still open. So for instance, to this date, it is still unknown what is the maximal distance between a d-dimensional norm and the L infinity norm. So this is one of the most important problems in the area.
Is the cube the only example where square root of d is necessary?
No. There is no somehow asymmetric result. But we have an understanding of how they look, but it's not just a cube. For instance, also the L1 ball, but there are other spaces too. But we know a criterion for when the answer, for instance, is little low of square root of d. So for when it goes to infinity with something slower, but I'll get to that. So let's go back to John's theorem. And I stated it as an isomorphism theorem, but let me just restate it now as an embedding result. Okay, let me introduce a little bit of terminology. A metric space M embeds into a non-space Y with by Lipschitz distortion at most D if there exists a mapping from the metric space into Y such that the distance in the image of f of x minus f of y can be squeezed between the distance in M of x and y and capital D times the distance in M. So this is the notion of a by Lipschitz distortion. It's the nonlinear analog of the bound for a linear operator that we already saw. And John's theorem trivially implies the following statement. Every d-dimensional norm admits a by Lipschitz embedding into the infinite dimensional Hilbert space L2 with distortion square root of d. Okay, now this is completely trivial given the previous formulation of John's theorem because there is a linear mapping to L2 of dimension d. So this statement from what we already saw as John's theorem is trivial, but it turns out that it's also completely equivalent. So if you just knew this weaker statement about the nonlinear embedding, you would be able to derive the fact that there is also a linear isomorphism with L2D. And the idea here is very simple, actually. So, suppose that you have your mapping F from the metric space, from the Norm space into L2. Then this is a Lipschitz mapping, and you can basically invoke Rademacher's differentiation theorem, well, for L2 valued mappings, but that's fine. Okay. So in particular, there exists a point in RD where your Lipschitz mapping has tangent. So at the first level of approximation, it can be approximated by a linear map. And this linear map is now defined in X, which is you identify with its tangent space, and takes values in L2. But since X is d-dimensional, then of course its image, or the image of the linear map is going to be at most d-dimensional. So you have a linear map now from a d-dimensional space to d-dimensional space, and you can check that the Lipschitz condition implies the same condition for the linear map. So in fact, just by differentiating at a point, and the point is given to you by Rademacher, you get that this nonlinear formulation is completely equivalent to the linear one. And now let's get the point of this talk. The point of this talk is what can you do to beat the square root of d barrier. As we discussed, the square root of d barrier is just there. The cube is an extra measure, so there's nothing you can do about that. There is an option to say, well, I'm going to look at Norm spaces that are more structured, but suppose we want something for an arbitrary Norm space. And then what you have to do is that you have to relax the notion of an embedding that you are interested in. So let me introduce the necessary formulation. So a metric space embeds into a Norm space, not with by Lipschitz distortion, but with Q average distortion D, if the following holds. Fix a probability measure mu on the space M. Okay, so fix a distribution between points in M, Then you can find a D Lipschitz map defined on the metric space with values in Y, but the D Lipschitz map now depends on the measure that you chose. And you don't require that the lower bound holds true for every x and y, but you just require that it holds on average with respect to the arbitrary measure mu. Okay, so before we wanted an upper and lower bound with respect to every x and y, here we want an upper bound for every x and y, and the lower bound which holds for an average, but with any notion of averaging you like. So by the way, here this means that there isn't an average distortion embedding. We say that a space admits an average distortion embedding, but there does not exist a single average distortion embedding, since it depends on the measure you chose. So this is the first notion, which is clearly a relaxation of by Lipschitz embeddings. The second notion which we're going to need is a fairly violent operation that you can perform on a metric space, which is to take the theta snowflake. So if theta is a number between 0 and 1, the theta snowflake of a metric space is the same set with its metric raised to the power theta, which is, of course, itself a metric, since theta is smaller than 1. Okay, and of course, the larger theta is, the closer to 1, the more you resemble the metric space you started with. Okay, so these are the two notions that we're going to need. And knowing these definitions, we can actually go and state now the main theorem of this talk, which is Naor's average-on theorem, which says the following. Take any d-dimensional norm, no matter what it is, then the 1/2 snowflake of it embeds with quadratic average distortion. By quadratic, I mean that the power is q. I should have said that before. The q average distortion was the exponent on the averaging. There's an exponent there, there's a degree of freedom. Here, so we're talking about quadratic average distortion, so average distortion with power 2, which is not square root of d anymore, but it's actually square root of log d up to a constant. Okay, so you basically have an exponential improvement of the John theorem, but it's an improvement within quotes because it doesn't imply it, of course, but with two major differences. First of all, you relax the notion of the embedding, and secondly, you replace the initial norm space with its 1/2 snowflake. So again, it's an improvement in this sense, and I am claiming that it is sharp in 3 different ways. First of all, suppose that you're interested in this statement with the word average replaced by Lipschitz. Okay, so suppose that you are interested in by Lipschitz embeddings of snowflakes of norms into L2. Then no matter what snowflake you take, you have to pay a polynomial factor in the dimension. So the theta snowflake of L infinity of dimension d requires distortion d to the theta over 2. So no matter how small theta is, you're going to have to pay a polynomial factor in the dimension. So you cannot get subpolynomial bounds without referring to average distortion. Secondly, suppose you are interested in average distortion, since we convinced ourselves it's necessary, and you ask, well, maybe 1/2 snowflake is unnecessary, or maybe I can snowflake less. That's not the case. So if you have the 0.50001 snowflake of some norm space, you are still going to have to pay a polynomial factor. So if you want the polynomial factor to become something subpolynomial, like square root of log d, you cannot snowflake less than 1/2. This is the least that you can somehow violate the initial metric. So both the assumptions are necessary, both taking 1/2 snowflake and doing average distortion. And finally, under those assumptions, square root of log d is the best possible distortion that you can hope. You cannot improve.
Instead of 1/2, you take something bigger, then it follows the default also?
No, so if you take something bigger, the bound becomes polynomial. If you take something something smaller, which means that you are violating the norm more, then it's not, I think it's not exactly known what the correct power is. So you would hope that as theta becomes smaller, then the square root of log d would also become smaller. But I think that the correct power is not known. No, I think not. I think not.
But does it follow that it also smaller than 1/2 because it's the same square root of
Okay. Okay. That's a very good question. Yes, but it's a non-trivial statement. So this statement is monotonous in the amount of snowflaking. So if you can prove it for 1/2 snowflake, you can prove it for 1/3. But this is a non-trivial theorem. So, and it actually relates to a very, very nice open problem in Banach space theory. So if you want to ask me at the end, I can say more, but indeed, so it's monotonous in the amount of snowflaking. Okay, so this is the statement of the theorem. So no more questions. Okay, my goal today is to A, convince you that this is interesting, and B, show you basically most of the ideas in this proof. But before, let me show you an application. And somehow the reason for which I understand was the theorem was devised or where it came from. I'll just speak a little bit about expander graphs. Now, let G be an R-regular graph. So I have vertices, I have edges, and by R-regular I mean that every vertex is connected to exactly R neighbors. And let's denote by A of G the normalized adjacency matrix. So the adjacency matrix is indexed by vertices of the graph, and the UV entry of the matrix is equal to 1 over R if U and V are connected by an edge, and 0 otherwise. So this is a matrix with non-negative entries. It's clearly symmetric, and also clearly by the assumption that it is R regular, that the graph is R regular, the rows sum up to 1. So this is also a stochastic matrix. And as a symmetric stochastic matrix, it has real eigenvalues, all of which lie between -1 and 1. So the top eigenvalue is 1, corresponds to the vector of all ones, and the lowest one is greater than or equal to -1. Now the quantity that's going to be interesting for us is the spectral gap. So the gap between the first eigenvalue, which is 1, and the second, which is lambda 2 of the graph. And actually I'm going to denote by gamma of G to be the reciprocal of the spectral gap, which can be infinity. And the standard definition, or maybe the less standard definition of expansion, is that the sequence of graphs, of R-regular graphs where R is fixed over N, is an expander graph sequence if the sizes of the vertex sets go to infinity, and moreover, the spectral gaps remain bounded away from 0. Or otherwise, the reciprocals of the spectral gaps, gammas, remain bound away from infinity. Okay, as we saw yesterday also in Vincent's talk, that this is equivalent to the combinatorial notion of expansion. So the idea is that you have a graph that, because it's a 4 regular, it's a pretty sparse graph, but at the same time you don't have a way to cut it into 2 pieces so that without having a lot of communication between the pieces. So by Giger's inequality, this is equivalent to the fact that even though the graph is sparse, then it's extremely well connected. And the application of the average-John theorem is that expanders are objects whose geometry is intrinsically high-dimensional. So this was proven by Noor a couple of years before by a different method. And says the following: suppose that you have an n-vertex connected 4 regular expander. Let me decompress the notation. R is equal to 4 just for simplicity, because I didn't want to track one more parameter. I'm going to speak about geometric properties of the graph, so I want it to be connected so that it's a metric space with the shortest path distance. So this is now a metric space. And finally, when I say, because before we discussed about sequences of expanders, so what do I mean by n-vertex expander? Well, I basically mean that I imagine n as being huge and the spectral gap as being constant, bound away from 0. Okay, so this is what I'm going to denote by n-expander. And the conclusion of the theorem is that suppose you can find a little d-dimensional norm, n norm in Rd, such that your expander with the shortest path metric embeds with by Lipschitz distortion capital D. Then the dimension, little d, has to be polynomial in n. So you cannot hope to embed an expander into any, say, log n dimensional space. You simply cannot cook up a norm like that. Now, something which is important here and interesting is that the dependence between the distortion, the dimension, and the number of points is actually completely optimal. So a classical theorem of Johnson, Lindenstrass, and Shetland from the 80s says that for any n and n capital D, absolutely any finite metric space on n points can be embedded into some norm space of this dimension, n to the universal constant divided by capital D. So the bound which expanders achieve is actually completely sharp by a very classical theorem. You cannot hope that these objects are more high-dimensional than they are. So in a way, they're the most high-dimensional metric spaces. And that's a comment for later, so I'm going to say now. Noor's theorem is going to be proven by average John. This theorem, the top theorem here is sharp, which by Johnson, Lindenstrass, Schachmann. And this also implies, going back, that the square root of log D in the average John theorem is sharp. Okay, that's just a remark. But the fact that Johnson, Lindenstrass, Schachmann exists means also that the initial average John theorem is sharp, and this follows from the proof that we're going to see. Okay, so Johnson-Lindau assessment is sharp, but this we already knew. So there's a very important theorem of Matuszek from 96 who basically invoked some ideas from algebraic geometry and constructed a beautiful family of random metric spaces for which he showed that this dimension in the JLS theorem is actually needed. But the difference between Matuszek and the theorem that we have now is that now at least there is a specific criterion of a space that's very well studied, and it's the property of having a spectral gap, which tells you that this space is intrinsically high dimensional rather than a specific example about very interesting of a high dimensional space. Okay, so now we have a specific criterion which enforces high dimensionality. Okay, and let me show you the proof of this theorem using the average John theorem just in a couple of slides. So take an n-vertex four regular connected expander. So I'm going to denote by gamma of g, I'm going to denote gamma by gamma of g, the reciprocal spectral gap, and I'm just going to think about it as a constant from now on. And let's just assume that there exists a d-dimensional norm such that an embedding f from the vertex set into this norm with distortion capital D. Okay, and now what I'm going to do is that I'm going to say, well, this d-dimensional norm, which was given to me by this theorem, by average John can be embedded back into Hilbert space. So by the average John theorem, I can find a reasonable embedding. But to find a reasonable embedding, I need to tell you what the measure is. Remember, there was a measure with respect to which you took the average distortion. Now the measure is going to be the push forward of the uniform measure on the vertex set inside X. So you have the uniform measure on the vertex set of the graph. This is mapped to a measure inside the norm space X. So look at this measure. It's 1 over n times the sum of the delta masses. And the conclusion is that there exists a Lipschitz mapping with constant big O square root log D. That's what average John tells you. It's defined on the 1/2 snowflake of the norm, takes values in L2, and satisfies the condition on average. So on the left-hand side, you have the average in the image, g of f of u minus g of f of b squared, because we're talking about quadratic average distortion. On the right-hand side, you have the average in the pre-image, which is f of u minus f of v. And now notice that because we are talking about quadratic average distortion, but of the 1/2 snowflake, the exponent on the right-hand side becomes 1. Okay, so the 1 in the exponent is because we're talking about quadratic average distortion of the 1/2 snowflake. Okay, but how are we going to use the spectral gap? Well, this is the main idea that was discussed also in yesterday's talk, that the spectral gap, and this is going to be also important later, the spectral gap, the classical spectral gap, has an interpretation as an optimal constant in a functional inequality. So gamma is the best constant such that any function h from the vertex of the graph into the Hilbert space L2 satisfies the following property. On the left, we have the average of h of u minus h of v squared, where u and v are uniformly random points chosen in the vertex set of the graph, is bound above by gamma, and then we have the average over h of a minus h of b squared, where now a and b are not general, but they're actually only the points that are connected by an edge. Okay, so if you're bored, you can actually take a pen and paper and prove this. This is actually a very simple exercise to prove that this is 1 over 1 minus lambda 2. It's just a linear algebra exercise we also proved yesterday. So this is exactly what 1 minus lambda 2 is in functional terms. And now let's just use this because we have a map from V into X. We have a map from X into a 2. So let's apply this inequality here to the composition G composed with F. Okay, this inequality that I just said is exactly the middle inequality in this string of inequalities here. So you see, the middle inequality from the first line to the second says that the average over all vertices is bound above by gamma times the average over edges. And now for the left-hand side, let me just go back. We want to bound this average of g of f of u minus g of f of b squared. This is exactly what's been done in these two inequalities here, right? So first, by the second inequality is bounded by the average of f of u minus f of v. And then you apply the lower bound, the lower Lipschitz bound for f, to show that this is bounded below by the average of the distances between u and v, where u and v are two uniformly random vertices in the graph. Okay, so this is just concatenating the two lower bounds so far, and notice that indeed we only used the averaged notion of the lower bound for g. And for the upper bound, well, what can you do? You can just use the Lipschitz conditions for U and F, for G and F. Now G is a big O of square root log D Lipschitz function. So because you have the square there, you're going to get a log D. But its values are in the snowflake. So what you're going to have is an average over edges of f of a minus f of b to the power 1. And a and b are connected by an edge. And since the function f was capital D Lipschitz, what you get here is gamma times d times log of little d. Okay, so this is truly something trivial. I don't know if it came across as that, but it is. So, okay, even if you get lost in computations, it doesn't matter. It won't matter anymore. Because we're basically done now. Because notice that the graph is actually regular. All we have left to do is estimate this average of distances on the left-hand side. The graph is actually regular, which means that, if you fix a point u, it has 4 neighbors, and therefore it has at most 16 points at distance 2 and 64 points at distance 3 and so on. So, basically log n for every u, there are basically log n points which satisfy that the distance from v to u is at least n over 2. Okay, so if you want to get n over 2 points, you have to do a radius of at least log n. So this average over here that we wanted to estimate is bounded below by a universal constant times log n, say log n over 100. And now if you look at this inequality and you exponentiate everything, what you get is that d is bounded below by n to a universal constant divided by capital D, which is exactly the high dimensionality of expander that I promised. So this is a situation in which a positive embedding theorem, Albert-Jones is a positive theorem. It tells you that every norm space embeds, becomes a negative embedding theorem. Because here you see that, well, expanders cannot embed because they simply do not have this property. Okay? So this is an instance where somehow good news become bad news. Is there any question about the? Okay. So this is the application about expanders. There were bounds on this question, what's the dimension in which you can embed expanders since the 90s through work of Lineal, London, and Rabinovich, and they were all logarithmic in the dimension or logarithmic squared. So this is the first time that a polynomial bound is achieved. And let's now start discussing the proof. Okay, and what goes into proving a theorem like Albert-Jones. And quite surprisingly, or maybe not so surprisingly, we'll go back to the notion of a spectral gap. But now we're going to speak about nonlinear spectral gaps, which were already on the title. Let me again introduce a little bit of notation. So let pi be a vector of n numbers, which I'll think as a probability measure on the set 1 up to n. So the pi i's are non-negative numbers, and they sum up to 1. And I'm going to say that the stochastic matrix is pi reversible if pi I aij is pi j ajI. Okay, and I'll demystify the condition just in a minute. The way we think of the matrix A is probabilistically. So the matrix A can be thought of as the transition matrix of a discrete time Markov chain with values on the set 1 up to n. So you have your n matrix and you say, well, I'm going to think of a Markov chain for which the probability of jumping from point I to point j at any time t, so it's a homogeneous time Markov chain, is exactly aij. And the reversibility, these are just classical stuff about Markov chains now, the reversibility implies that the measure pi is stationary for the chain, meaning that if you distribute the first step of the chain x0 according to pi, then xt is distributed according to pi for any time t. But in fact, reversibility means more than that. Reversibility means that you can actually go back in time, so that moving forward in time is equivalent to moving backwards in time. So this is the probabilistic interpretation. But we are not going to use that. What we're going to use is the analytic notion of reversibility, which is that since it's reversible, it defines a self-adjoint operator on r to the power n, but with the following Hilbertian structure, the L2 of pi structure, whose norm is given by what's written here. So some pi I xi squared rather than the sum of xi squared, and therefore it has real eigenvalues again between -1 and 1. And as in the case of regular graphs, we are going to be interested in gamma of A, which is the reciprocal of the spectral gap. Now, by the way, the case that A is the adjacency matrix of a regular graph is a special case of this. So again, we're going to be interested in this quantity gamma. And once again, this quantity captures the best constant in a geometric or functional inequality, depending on how you view it. So it's the least constant, such that for any points x1 up to xn inside L2, the sum over I and j, pi I pi j, xi minus xj squared. This is basically the uniform average, but uniform now with respect to the measure pi, is bound above by the sum over I and j, pi I aij, xi minus xj, which is basically the quantity which measures in expectation squared how much the Markov chain moved from step 0 to step 1. Okay, so what this is the distance, is how much the Markov chain moved in one step, and therefore it's exactly the analog of measuring the distance along edges in the case of a regular graph, if you have the standard random walk on the graph. So again, gamma is the best constant here, and the moment you see this inequality, there's an immediate generalization, and the question is why this generalization is interesting, but we're going to address this in a minute. The generalization comes from the natural question, which is, why do we care about L2 specifically? What is special about L2 in the statement? So take a metric space, take a power p, and then for any pi reversible stochastic matrix, I'm going to note by gamma of the matrix with respect to the distance to the power p to be the best constant such that this inequality is satisfied, but not for any endpoints in Hilbert space, but for any endpoints in my completely arbitrary metric space where I replace the power 2 by power p. Okay, so far this is a completely legitimate definition. I'm just defining it as a best constant. This is called a reciprocal to a nonlinear spectral gap. Nonlinear refers to the fact that we are living the real line or Hilbert space, and we are being in an arbitrary metric space and with an arbitrary exponent. Okay, so this quantity gamma of A with respect to the distance to the p is going to be the central quantity for the rest of the talk. And the major open problem here is in which instances can the nonlinear spectral gap constant be controlled by the regular spectral gap constant with any reasonable notion of control, any function psi. Okay, so when does an algebraic spectral gap tell us that we have this geometric inequality on the spacetime? So this is basically a level of complexity higher because this quantity, the nonlinear spectral gap, tries to understand the interactions of the spectral properties of the matrix and the geometry of the metric space. I should say that an opposite inequality always holds. So if you have a nonlinear spectral gap with any metric space, with at least 2 points, so that's non-trivial, then you automatically have a regular spectral gap. Okay, so this is something that's genuinely more complicated, and the class of metric spaces for which we know inequalities of this form is still extremely, well, it's not what we would want it to be. There are still very few examples for which we know statements like that.
And the reasonable recension of the metric space, why does the argument you said at the beginning, linearization argument?
What do you mean by linearization?
The argument you said that at the beginning of the book that we have the linear result, get the general one, an argument just to
Oh, because there is no notion of there's no notion of a tangency even. A priori, no. That's okay. That's actually a good question. So, in principle, under smoothness assumptions and correct curvature bounds, then yes, then we know it. So, for instance, in non-positive very good question. Thank you. So, in non-positive curvature, you assume that you have something like a Hilbert manifold or Finsler with some assumptions on the tangent space and so on, then you can actually get statements like that. So yeah, I agree. Thank you. So indeed there are cases where we know it, but for instance, if you wanted to do this for every cat-zero space, so without introducing smoothness assumptions, then this is a major problem. Okay, and I'm going to address just one technical fact about this quantity, about this constant, which is the property of extrapolation. And what this means is, how do these constants depend on the power p? Okay, so there was a power that was arbitrary in the nonlinear spectral gap inequality. So let's just see the technical fact of how they depend on the power p, at least in the case of Norm spaces. And this is well understood in the case of Norm spaces. So for just the norm being the real line, this was done by Matuszek in 1997. The vector valued version is due to Tim Delat and Michael de La Salle from a few years ago. And the statement is that if you have any norm space and p smaller than q, then the nonlinear spectral gap with power p is bounded above by the nonlinear spectral gap with power q, and bounded below by the same quantity but raised to the power p over 2. And the powers here are both optimal. So there isn't something which you can do to improve those powers, but we know that at least if one of them is finite, then the other one is finite as well. Okay, but we are going to see later that very often the power actually matters. Okay, but at least we know that they are equivalent in this reasonably weak sense, so at least in the range of the open problem that they posed before, at least when we speak about norms, the choice of the power doesn't matter. Okay, and there's a lot of information, basically the survey which is basically about nonlinear spectral gaps rather than the average John theorem. The average John is an excuse to present the theory. And in the last section I put basically a range of applications of nonlinear spectral gaps in various areas of math. But this is all that we're going to need at this abstract level. And now we're going to go back to our problem, which is how do we get an average distortion embedding. Now, let me tell you one connection of nonlinear spectral gaps with average distortion, which is completely trivial. So this slide is completely trivial. Okay? Suppose that you have a metric space which embeds into a norm space with Q average distortion. And let A be a pi-reversible stochastic matrix. And you want to argue about the nonlinear spectral gap of the matrix with respect to the metric space compared to the one with respect to the norm space. So take n points in your metric space M, x1 up to xn. And then use the average distortion embedding assumption with respect to the measure pi, the stationary measure of the matrix or of the chain. And then you deduce that there exist points in y, y1 up to yn, which satisfy the D Lipschitz condition. So yi minus yj is bounded by capital D times xi minus xj. And you have the lower bound only on average but with respect to the probability measure pi. This is what you get from an average distortion embedding with the measure pi. And then, well, suppose that you want to control this quantity, the sum pi I pi j distance of xi xj. Use the lower bound first that we just got from the average distortion embedding, and then employ the nonlinear spectral gap inequality in the normed space y rather than the initial space x. So what you get is gamma of A with respect to the norm to the power q times the sum pi I aij times yi minus yj to the power q. Okay, so first I'm employing the lower bound by average distortion, and then the nonlinear spectral gap inequality in y. And now all you have to do is use the Lipschitz condition. So yi minus yj is boundable by d times xi minus xj, and you conclude with this inequality. So if you take a supremum over the xi's, then you get that the nonlinear spectral gap of A with respect to the distance to the q is boundable by d to the q times the nonlinear spectral gap of A with respect to the norm to the power q. So all that I proved in this slide, which again is trivial, is that nonlinear spectral gaps with the correct power are inherited by average distortion embeddings with the same power. Okay, and the factor, the multiplicative factor, is the distortion to the power q. Okay, it's clear? Good. Now, the relevance of nonlinear spectral gaps in the theory of average distortion embeddings comes from something called Nauer's duality principle, and it's the surprising fact, a priori surprising at least, that this was actually an equivalence. That by comparing nonlinear spectral gaps, you actually didn't lose anything. And this is a theorem which he proved in 2014, and says the following: suppose that you have two parameters, q and d, and let M be a metric space and y be a Banach space, such that we have the comparison inequality for nonlinear spectral gaps. So the nonlinear spectral gap of A with respect to the distance to the q is bounded by capital D to the q times the nonlinear spectral gap of A with respect to the norm to the q. Then the conclusion is as close as it can be to the fact that M embeds into a q of y, into y with distortion D. Okay, so the real statement is that taking epsilon, you can embed M into some ultra power of LQ of y with distortion D plus epsilon for any epsilon. Now, just comment on what's meant here. Of course, LQ of y is a space of q summable sequences with elements from y, and the nonlinear spectral gap with the norm to the power q is invariant under taking LQ sums. That just follows from the definition. So you have to tweak your space by taking an LQ power because, for instance, y could be the real line here, and you couldn't hope for embedding in y then, by no means. So you need to go to LQ of y, and then you prove the statement with LQ of y for every finite subset of your metric space. Well, to argue about the whole space, you need to take an ultra power. But that's kind of abstract nonsense. Somehow the crux of the argument is the finite subset case. And the proof is basically one page. It's in the survey, you can read. And it's a clever Hahn-Banach separation argument. Let me just say a word about how it goes. Suppose that they give you a finite metric space. M is an n-point metric space. So as an object, it's completely determined by the n by n matrix, which is the matrix of distances. Okay, the distance from xi to xj. And this completely determines the geometry of the space. Well, admitting an average distortion embedding is completely equivalent to the matrix of distances to the power q. So you raise every distance to the power q inside the matrix, belonging in a certain cone on the space of matrices. So saying that you admit an average distortion embedding is equivalent to the matrix of distance to the power q belonging in a special cone inside the space of matrices. And then you go by contradiction and you say, okay, let's suppose that it doesn't embed. In other words, let's suppose that the matrix of distance to the power q does not belong in that cone. Then, by Hahn-Banach, you find the separating hyperplane. And then if you write down what the separating hyperplane condition is, it exactly violates the nonlinear spectral gap inequality. Okay, so this is the argument that you can see it written. It's really short, but really, really beautiful. And then to go to the infinite case, you take an ultra power. Okay, you do so. But the crux is the finite dimensional case. So this is the comparison. This is where nonlinear spectral gaps pop in. Because notice that for us, the metric space M is a d-dimensional norm space. The distortion is, okay, big O square root of log d. 2 is equal to 2 because we are talking about quadratic average distortion. And Y is simply the Hilbert space. So in view of the duality principle, average John is completely equivalent to a nonlinear spectral gap estimate. Let X be a finite dimensional norm. Then for every n, every reversible matrix, the nonlinear spectral gap of A with respect to the norm. Notice that the power here is 1 because we talked about quadratic average distortion, but we have the 1/2 snowflake, so the power actually becomes 1, is bounded above by the square of the distortion. The distortion was square log d, so this becomes log d, times the classical spectral gap of Hilbert space, which is 1 minus lambda 2. So the average John theorem is completely equivalent by this duality principle to this estimate for nonlinear spectral gaps of finite dimensional norms. And are there any questions about this statement? Okay, if not, I'm actually going to move on to the blackboard and prove this theorem for you. Let me know if I need to write larger or something. So I have to prove that this is bounded above by log d divided by 1 minus lambda 2. Okay. Is this visible in the back? Okay. So let's see, how do we control a nonlinear spectral gap inequality? Now we have to move on to a geometric argument rather than something spectral. So let's take points x1 up to xn in Rd, and we want to, let me maybe go back to the definition of the constant so that we see it. Where is it? Here. Okay. So we want to bound from below the sum over I and j, pi I aij, the norm of xi minus xj. Okay, the power is 1 and the norm is arbitrary. Okay, so I'm going to do a very simple trick first. I'm going to replace aij by aij plus the Kronecker delta delta ij over 2 times xi minus xj. And the reason I can do that is that when I is equal to j, this quantity becomes 0. Okay, so what I'm doing at the level of the Markov chain is that I'm basically making the Markov chain lazy. So I'm making it stay fixed with probability 1/2. Okay, and you have to multiply by a factor of 2. So this is just equal to the expectation, probabilistically, f at time x1 minus f at time x0, maybe twice, where xt is a Markov chain with transition identity plus the matrix over 2. So I'm just rewriting this object probabilistically the way I explained before. So what this is exactly that. Okay? And notice that xt is distributed uniformly according to the stationary measure. And therefore, by a simple application of the triangle inequality, notice I want to bound from below. This is bound below by 2 over t times the expectation of the norm f of xt minus f of x0. Why is that? Well, if you want to figure out how much the Markov chain wanders in t steps, since everything is distributed according to the stationary measure, this is going to be at most t times how much it wanders in one step. So I'm just applying the triangle inequality in stationary here. So you go from, xt to xt minus 1, xt minus 1 to xt minus 2, and so on. And then you apply that everything is stationary. Okay? And now what is the matrix? I want to rewrite it like this. What is the matrix of the Markov chain xt? Well, what it is simply this to the power t. So that's 2 over t, sum over I and j, pi I. So this is going to be a plus identity over 2 to the power t ij, xi minus xj. The matrix of this chain, which jumps from x0 to xt, is the initial matrix raised to the power t. And if you rewrite now everything with respect to nonlinear spectral gaps, this tells you that gamma of A with respect to the norm is bound above by t over 2 times gamma of A plus identity over 2 to the t with respect to the norm. That's what we just proved. You just go back, figure out what this means in terms of the constants, and that's it. And that's true for every t. I haven't told you what t is yet. Okay, we're going to have to be careful when we choose it. So it's an infimum over t. And I have to say that everywhere in the literature, this trick of somehow working with the power of the matrix, everywhere it's attributed to work actually of Vincent Lafort. So we have this, and now I'm going to do one more thing. I'm going to use extrapolation. Because remember that if I increase the power here, I can increase the spectral gap just by a constant. And I'm going to, sorry, that's the matrix A plus identity over 2 to the t. And here I'm going to replace power 1 by power 2. So bounding this quantity, to bound this quantity, it suffices to find a large enough t so that I can actually control this quantity here. And what's the idea, basically? The idea here is that if you take a large enough power, this comes much closer to stationarity. So if you can argue that for a large enough power t, this quantity is a constant, then hopefully you can get a reasonable bound. Okay, so let's do that. Let's control this. So let's take points y1 up to yn in Rd. Now I want to check, I'm going to denote this matrix here by B. And I now want to control the nonlinear spectral gap of this. Now notice that in the definition of nonlinear spectral gaps, if we have a norm, we are free to translate our vectors xi, now I'm going to call them yi, by the same additive constant, because the only thing that appears is yi minus yj. Okay, so without loss of generality, I'll assume that the sum over I pi I yi is equal to 0. So I'm just going to center the vectors, which I can do simply by translating. And I'm going to introduce also a little bit of notation. So if y is the vector y1 up to yn, this is a vector of vectors now, I'm going to denote the L2 of pi x norm of this as the sum pi I yi squared square root, the vector valued L2 norm, where I have the norm in x, and I'm going to look at the action of the matrix B on y in the usual way. So if this was a vector of numbers, I could multiply it on the left with matrix B. Well, I can do the same with a vector of vectors, and what I get is a vector. Okay, and maybe, no, I won't need anything else. Let's just see. Too high. Okay, good. So there's a little bit of notation. And now let's see. So what we have to do is we have to bound the sum over I and j to n pi I bij yi minus yj squared divided by the sum over I and j pi I pi j yi minus yj squared. Okay, so to get a bound on the nonlinear spectral gap constant, I need to bound this quantity from below. Okay, so I'm going to do that, and I'm going to apply an inequality on the numerator and an inequality in the denominator. So let me just start by bounding the denominator from above. Okay, and that's going to be very simple. This is bound by the sum over I and j twice pi I pi j norm of yi squared plus norm of yj squared. Okay, so I apply the triangle inequality. This is bounded by the norm of yi times the norm of yj plus the norm of yj, and then I put the square inside, you lose a factor 2. Okay, so far I did nothing. And here I'm actually going to do something slightly smarter, which is that I'm going to use that this matrix B is a stochastic matrix. Okay, so B is a power of the stochastic matrix A plus I over 2, and therefore it is itself a stochastic matrix. So the sum over j of bij is equal to 1, and therefore you can move inside the square of the norm by Jensen. So this is going to be a sum over I, pi I, the norm, and then I'm going to move inside the sum over j bij. This won't affect the yi because the bij is sum up to 1. So this is going to be yi minus sum over j bij yj squared. Okay, so I moved it inside just by Jensen and by using that stochastic matrix. And now let's just see. In the denominator, when you sum, for instance, the first terms, the sum over j disappears because the pi j also sum up to 1. So what you have is that this is the L2 of pi norm of the vector y. And same for the second term. So the denominator is going to be 4 times the L2 of pi x norm squared of the vector y. And in the numerator, what we have is yi minus the ith entry of by. Okay, so what this is y minus by L2 of pi x squared. Okay, and now I'm going to do one more thing. I'm going to apply the triangle inequality on the numerator. So on the numerator, I can bound this above by the norm of y minus the norm of by. That's everywhere, L2 pi x, L2 pi x, divided by the norm of y, L2 pi x, square. just applying the triangle inequality, and note that what's in here is actually positive, and therefore I didn't cheat by taking the square. Okay, and now we're basically done, because this is 1 minus the norm of by in L2 pi x over the norm of y in L2 pi x squared. So to bound this from above, we have to show that by over y is bounded away from 1. Okay, and this is very much consistent with the fact that we want to control a second eigenvalue. And now you see why I normalized for the sum of pi I, yi to be equal to 0. This means that you are orthogonal to the eigenspace of the first eigenvalue, right? But we have no way to do it because we are in X. We are an arbitrary norm. There is simply no way to argue with eigenvalues. But let's go back to the start. So by the classical John's theorem, we can find a Hilbertian structure I'm going to call it just absolute value in RD, such that this is bound above by the norm is bound above the square root of d times this. And therefore this ratio of norms in here is definitely bounded above, bounded below, if you just lose a factor of square root of d. And you replace the x L2 of pi h L2 of pi h, and I'm going to put a plus because I can only do this if what I have inside the parenthesis is positive. But so far I'm just saying that the ratio of these things is at most square root of d times the ratio of those, just because the two norms are actually equivalent. But now this is great, because this is a vector of vectors that is orthogonal. It's in a Hilbert space now. L2 of h is a Hilbert space, and it's orthogonal to the first eigenvector. And therefore now I can simply apply the spectral estimate. So this is boundable by 1 minus square root of d lambda 2 of the matrix plus squared. And what is lambda 2 of the matrix? Well, the matrix will power. So that's 1 plus lambda 2 of a over 2 to the power t plus squared. And now you notice here maybe why I also, at the very first step, I consider a plus I over 2, because here otherwise it would be the maximum absolute value of an eigenvalue. Whereas by this trick everything is positive definite. Okay, so that's the estimate that we get. So now what you have to do is to choose the smallest t star such that square root of d 1 plus lambda 2 of a over 2 to the t star is smaller than 1/2. Then by this chain of inequalities, the nonlinear spectral gap a plus I over 2 t star with respect to the norm squared is a universal constant. And therefore, by the inequality above, over there, the spectral gap that we wanted is bound above by t star. And now you have to figure out what t star is by solving this. But this is indeed, so this is something that you can check. By solving this inequality here, log d over 1 minus lambda 2 of a. And this is the spectral gap estimate that was equivalent completely to the average John theorem. So the idea here is take a power. I should make one very last remark, very, very quick. So if you invoked the average John theorem at the level of, the standard John theorem at the level of definitions of nonlinear spectral gaps, you would have taken, so if you start from the definition of nonlinear spectral gaps and say that, well, at this level here, I replace the norm by the Hilbertian norm, you would actually lose a factor of square root of d. Okay, so if you do it from the beginning, actually d, because everything is squared, you would use a d, you would lose a d. So the important here is that if you rewrite everything in terms of the operator norm of the adjacency matrix, and you take a suitable power with respect to which you optimize, then by optimizing over the power, you actually get the correct bound, which is log d times the classical spectral Good. And that's the end of the proof of the main theorem. And thank you. Okay, that's it.
Thank you.
It's a minor one, but I guess I missed the place in the last argument where you use this trick that you can translate by the identity.
Yes.
So it works. I understood why it works, of course, but where do you use it?
Yes. So, in principle here, when you want to control this ratio, y could be the first eigenvalue of the matrix. In which case, this ratio could be 1. So is this what you mean, where we use it? Because we use it here. Because by translating y, we make sure that this vector y is orthogonal to the first eigenspace, and the first. Okay.
Je pense qu'on peut remercier Alexandros again pour.
So this is the first time that a polynomial bound is achieved. And let's now start discussing the proof. Okay, and what goes into proving a theorem like average on. And quite surprisingly, or maybe not so surprisingly, we go back to the notion of a spectral gap. But now we're going to speak about nonlinear spectral gaps, which were already on the title. Let me again introduce a little bit of notation. So let pi be a vector of n numbers, which I'll think as a probability measure on the set 1 up to n. So the pi i's are non-negative numbers, and they sum up
Okay, so it's my pleasure to introduce the second speaker for this session, Ursula Menscheit, who will talk about local Morse-length rigidity. Thank you.
Yeah, thank you very much. It's a great pleasure to be here and report on the fantastic work of Guillemot and Lefebvre on what's called the Mark-length spectrum rigidity, but let me start with introducing the result. So what does the result say? You start with a closed manifold with a Riemannian metric. And if you have such a closed manifold and a Riemannian metric, you can associate to a conjugacy class C in the fundamental group of M a number, and the number is the length of the shortest representative of this conjugacy class. So let me call it L, G, or C, the shortest length of a representative of the conjugacy class, or meaning-free homotopy class. So what does it mean is you obtain a function which goes from C equal to the set of conjugacy classes into the, say, non-negative fields. So let me call this function L from C, or LG from C to this, the non-negative fields. And now if we look now at a manifold where the curvature is negative, strictly negative, then we know that each C has a unique geodesic representative. So in other words, we understand this function much better than in the general case. And there's the conjecture which says the following. So we have the section curvature negative, and if G not G are two such metrics, and if LG naught is equal to LG, then G and G naught are strongly isometric. So what does it mean, strongly isometric? There exist, oops, sorry, it was not good. There exists a diffeomorphism phi from M to M such that phi star G is equal to G naught. So the diffeomorphism group acts on metrics. You can take your metric, you can pull it back with a diffeomorphism, and then you get an isometric metric. And conjecture says that if we have two such metrics, such that for which the functions are the same, and we want to require that the curvature of G naught is negative, then actually these metrics are isometric, meaning that the metric can uniquely be characterized by this function LG. Yes, strongly isometric, meaning that a diffeomorphism isotopic sends you to the identity. Thank you. Sorry? Yes, 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 yes.
It's stronger than homotopic.
Yeah, it's stronger than homotopic. So that's the conjecture. So here's a theorem that is due to Guillemot and Lefebvre. And this was published in 2019, and which says this is locally true. So if G naught is, and now there's a small variation on the assumption, which I will explain in a moment, is non-positively curved. And if, and now I should bring this back here. And if the geodesic flow is a north of the geodesic flow of G naught, then there exists a neighborhood of G naught in the space of metrics in the C and alpha topology. And the n is some number which is can be established from the dimension of n of the manifold. N is bigger than 3 over 2 n plus 8, such that if LG naught is equal to LG, and if G is contained in the neighborhood, then it is true. And the conjecture is true. Meaning that if the Mach length spectrum in the sense, if these two functions are the same, then actually the metrics are related by diffeomorphism, which is isotopic to the identity. Now, what does it mean in loss of geodesic flow? It means that you have the unit tangent bundle of M. For the metric G naught, we think of it as the metric G naught is the one we try to study and where we want to study the rigidity for G naught. So we have the unit tangent bundle of M G naught, and we require there exists a decomposition of the tangent bundle of T1M as follows. This is equal to Rx plus E plus E minus. What is Rx? X is the generator of the geodesic flow. This flow maps a unit tangent vector as follows. So it maps it to gamma v prime of t. And I don't write this down. Gamma v is a geodesic with initial velocity v. So we start off with a vector, we translate it along the geodesic, we wait until time t, we get a new tangent vector. And this is the image of the geodesic flow. And E plus, E minus, so they're complementary to this, but we have for some norm on this the tangent bundle of the unit tangent bundle of M, so we can in some sense be flexible with the norm this T1M is compact. We have that there exists a number nu bigger than 1 such that so we take d phi t, so we take the differential of the flow applied to W, and this is supposed to be less than e to the power minus nu t norm of W if W is in E minus, so we have this decomposition here, and t for all t, and d phi t W is less than equal to minus nu of minus t. So I write this down in a complicated way to see that you invert the time here times W with norm of W if W is in E plus. So that means that the flow, the differential of the flow applied to the bundle E minus is contracting. The differential of the flow applied to the bundle E minus is contracting in the backward direction, meaning it is expanding in the forward direction. Nu is bigger positive. Thank you. Thank you. So that is more general, slightly more general than being negatively curved. It is not hard to see that if you have a negatively curved metric, then this situation holds true. But the importance here is that the proof of the Fervor and the GMO's theorem relies on analyzing this Anosov geodesic flow on the unit tangent bundle of M. Now let me summarize earlier results, which are important because they go into, in some sense, into the proof. So earlier results in this direction are due to a number of people. And you will clearly see that somehow the situation stops about more than 20 years ago. So there's the first theorem of Cutoff, which says that if the curvature of G naught is negative, and if G is of the form e to the power phi times G naught, that means G is a conformally equivalent metric, not necessarily close to the original metric, then the theorem holds true. That means if LG naught is equal to LG, then G and G naught are strongly isometric. Yeah, they're the same. So, so strongly isometric, meaning you basically you transform them as a diffeomorphism that is sort of a little bit sort of weaker than what I just said, being the same. So somehow here in the statement in the text, I write with a diffeomorphism, which is the identity. But that's sort of a weaker statement, and for the purpose of the talk today, I stated in this form simply because, I mean, this is a weaker conclusion. The metrics are isometric with a diffeomorphism to be consistent with what I had, what the talk is all about. Does it make sense? So the identity is a diffeomorphism, which is isotopic to the identity. That is what I'm saying. And here I'm just stating it again. I stated in this form for the sake of the talk today because I want to be completely consistent from the very beginning to the end. Okay. So that is the result of Cutoff. And so then there's a result of Ortal and Cook independently about 1990, which said the conjecture, not just the local statement, the conjecture stated above is true for surfaces. That means in the case that n is equal to 2. And the proof uses the fact that we have surfaces in a very strong way. And so there's these works here resulted in another conjecture, which let me state like this. So there's a stronger conjecture which says the following. If LG naught is less or equal than LG, then the volume of G is bigger or equal than volume of G naught, and equality holds if and only if G and G naught are strongly isometric. Yeah, so here's the curvature assumed to be negative. Strictly negative. Again, so the reason why I state Guillermo and Lefebvre's theorem in the form that they prove it is to focus on the Anosov flow. The conjectures here you would really require maybe that one of the metrics is strongly negatively curved, just to be safe. But it's a conjecture. There's no, there are no strong results in this direction. let's say the curvature of G naught is negative, strictly negative. And so the only global result is a result where I guess I have a contribution and then the so-called Valcalo. Which says that conjecture 1 is true if G naught is locally symmetric. So that is, I guess, in higher dimension, the only global result that is known to date. And now let me focus on the proof of the theorem of GMO and Lefebvre. So there are 3 steps in the proof. The first step is goes along more or less standard lines to overcome a certain difficulty, which I will explain next. The real innovation is second step, which is unexpected, I think, and a really cool idea. But let me first, to get the setup correct, let me focus on the first step. The first step is the diffeomorphism group. Control the action of the diffeomorphism group. Why do I need to do this? Again, the diffeomorphism group acts on metrics. That means I can take my metric, pull it back with a diffeomorphism, I get an isometric metric, and that's completely uninteresting. These metrics are isometric. So I need to understand the action of the diffeomorphism group on the space of metrics to obtain a global rigidity result. And so how do I do this? So the usual approach to this would be I find somehow in the space of metrics, I identify the orbit, the metrics that are identified with the diffeomorphism, which is isotopic to the identity. So I identify the space, and then I take a transverse space in the space of all metrics, which is an infinite dimensional vector space, or say a convex subset of an infinite dimensional vector space, and try to understand what's going on there. Well, that is the usual approach, and this works. And we need here to be a little bit more specific how the setup of the slice is going to be. So let me explain what the slice is. So now you have, again, you have a diffeomorphism, which is isotopic to the identity. And now we know it acts on the space of metrics. And now we understand what, and I'm introducing now some notation, acts on, what? Not only on the space of metrics, but also on the tangent space of the space of metrics, which is a space of sections of the bundle S2 of T star M. What is this? This is a space of symmetric tensors, 2 tensors, which define you bilinear forms on the tangent bundle of M. And so that is the tangent space to the space of metrics. If you have a metric, then you get a positive definite bilinear form, but the tangent space of the space of metrics doesn't require anything like this. So now what we could do is, we could take the Levi-Civita connection of the metrics. So we start off with our base metric G0. This will be fixed now for the moment, where we try to study this problem. And we look at the symmetrization. We have a symmetrization operator, which goes from, say, C infinity of, and let me just check which notation I took. So let me write it down local, sort of in pointwise coordinates. Goes from the tensor product, the M plus first tensor product of the unit tangent of the cotangent bundle of M to its symmetrization. So Sm plus 1 of this tensor of the tensor product. So these are symmetric M plus 1 forms on the tangent bundle of M. And so we can compose the Levi-Civita connection with the symmetrization. And now we think about it as going from the sections of T star M to the sections. So now we have here smooth sections of S2 T star M. So the covariant derivative is a derivative that means it maps smooth one form, say, which is a section of T star M, to its covariant derivative where you have an additional input in the data. And so then you symmetrize and you get here a section of the symmetrization, which is a C infinity of S2 T star M. Now if we do this, then we can look at this operator here. So let me call it delta star. The star comes for a more historical reason. And now what we figure out is to compute that this image here. And what is the image? We compute that delta star of alpha is minus 1/2 L alpha sharp of G naught. So we look at this Levi-Civita connection for the metric G0. Now this formula says the following. So L alpha sharp is a Lie derivative along the dual, the G0 dual of alpha. So here we make out of the one form a vector field, then we have the Lie derivative, and we compute that d star alpha is equal to 1/2 of this expression. So now why is it good? Because it explains to us that the image of d star, this is a tangent to the action of diff. So if we have here this flow given by this vector field alpha sharp, then it moves the metric, and this gives you deformation of the metric. And now we see here that we are in the image of the action of diff, meaning that here we pick out the tangent space in this, under the action of the diffeomorphism group. So this is the one, these sections that we want to discard if we want to produce a slice theorem which is transverse to the action of the diffeomorphism group. Now, let me take the formal dual, or the formal adjoint, delta of delta star. So this operator here acts on sections where we can put the sections with the L2 norm on. So we have an inner product on these tangents, on these tensor spaces here. We can look at the L2 inner product for sections. And so we have a formal adjoint delta of delta star. And what is this formal adjoint? Delta F is equal to minus the trace of the covariant derivative of F. And the trace is taken in the first two variables. So that's a differential operator, and we say that F is divergence free. If and only if this delta F is equal to 0. And why is this great? Because the composition of delta and delta star is an elliptic operator. So fact, delta composed with delta star is elliptic. And this means we can use PDEs to study the image of delta star, which is our enemy, and to try to understand how we produce a good slice theorem. And so what we get is, if we study this elliptic operator, we get the following result, which is due to Krog and Sharafutinov. And they prove the following using the ellipticity of this operator. Shafarutdinov. So that's it for F in, now we have some regularity of which I may not wish to specify here. So we look at symmetric section of the space of two tensors on M. And for this, such an F admits a decomposition, which is unique. Of the form F is equal to Fs plus delta star P. So we decompose our F into a component which is in the image of the delta star, which corresponds to looking at the diffeomorphism group, and some other component F. So delta Fs is equal to 0. And furthermore, we get a norm estimate, which is the norm of Fs. This is back now to some C and alpha norm on, I don't write it down on what the space of sections here is less or equal than uniform constant times the norm of F. So in other words, we have here also a quantitative statement, meaning that we can compute or estimate C and alpha norms in this decomposition here. So why is this great? Because it allows us now to produce a slice theorem, which is due to Guillemot and Lefebvre, which I abbreviate now by GNL. So what the proof is, so there are constants which I will not write down here for the sake of abbreviation. So what the proof is, if G0 minus G, again the assumptions here are standing that we have a non-positively curved metric now with an also geodesic flow. Think about it that G0 has negative curvature for simplicity. Then if this is less than epsilon, so that proves the existence of an epsilon like this, then there exists a unique diffeomorphism which is isotopic to the identity, close to the identity. So not only it's isotopic to the identity, but it's also close to it, to the identity, such that phi star G, so this is a metric we are studying, which is unknown. We think about this G0 as being the base point. So phi star G minus G0, this is now a section of the space of two tensors over the manifold, which is symmetric. This is divergence free. So that's the slice theorem that we wanted. With respect to G0, of course, because divergence free only makes sense if we fix the base metric. And furthermore, we need an estimate here, and the estimate is phi star G minus G0. So is in the C and alpha norm is less or equal than C times G minus G0. So this is exactly the slice theorem that we were looking at. We were looking at identifying the action of the diffeomorphism group in some quantitative way, given an unknown metric G, and we think about that these divergence-free tensors give us a slice transverse to the action of the diffeomorphism group, which we need to study. So now let me point out that there's another theorem which is due to Krog and Shafarutdinov, and this gives you an important idea how to use a theorem like this. And what they prove is, again, with the usual assumption, take F in now such a tensor field, symmetric tensor field, And now you think about this being a tangent vector to this space of metrics on your manifold. So now what the proof is, assume that define f of vv, pi of f of v is equal to f of vv. So we can apply this bilinear form here to two copies of v, so that's a unit tangent vector. So v is in T1m for the metric G0. And we define here a function on T1m by just plugging in two copies of v. That's a beautiful function. And now what the proof is that the following holds true if f is divergence free. Well, maybe I should formulate it slightly differently. If the integral over each closed geodesic of pi f, so that's now a function on the unit tangent bundle of M, is equal to 0 for all closed geodesic gamma. Then we have that this is really infinitesimally in the image of the diffeomorphism group. So the conclusion is that f is equal to ddt psi d star of G0 for a one-parameter family. Of diffeomorphisms. Now, what does this give us? So that is an important insight, which is the foundation of the work of Guillermo-Lefebvre. So what it tells us is, first of all, infinitesimally, the conjecture is true. So if we have such a tangent space whose integral is 0, integral over each closed geodesic, then we are actually in the orbit of the diffeomorphism group. So that proves the infinitesimal version of the theorem. However, it's very far away from giving the local version. But what it also shows you is how to understand the situation here. Namely, what you think about it is, how do we understand functions here that come from symmetric tensors which integrate 0 over each periodic geodesic. So we think about it, such a function pi f as a function of the form x of g for another function g. So we have this linear, one first order differential operator, which is the generator of the geodesic flow. If we take a closed orbit, then it means we just take the tangent of this closed orbit, we differentiate the function. And of course, if we have a function on, say, S1, and we differentiate it, and we integrate the result, we get the 0. This integral over a closed orbit will be 0. So now there's a Lifshitz theorems, a variety of Lifshitz theorems which tell you that if you have a smooth function which integrates to 0 over each periodic orbit of the flow has very rich dynamics, then it will be the differential of another function. So this means what we need to understand here is we need to understand whether we can prove a decomposition theorem of this form here, but where we now replace the differential operator, the elliptic operator, the star, by something else which comes from the differential operator x, which is first order. So first order is bad, it's not elliptic. But now we like to think about it that we try to produce a slice theorem in the following form. So we have this first order differential operator. We look at its range. The range should be, in some sense, complementary to those functions that come from divergence-free tensors. So divergence-free tensor fields are the ones due to the slice theorem that we want to focus on. But now we have to understand how this is going to go. And the main difficulty is how do we deal with the fact that this is the first order operator where we have no control. And this is the main advance in the work of GMO and Lefebvre, namely they use microlocal analysis to study exactly this operator and get the program that I try to indicate going. Now let me talk about the X-ray transform. So what does it say is we try to translate our problem that comes from integrating something over periodic orbits into something else where we can do honest analysis. This is what I try to indicate. In order to set this up, let us just look at the following. We look at an operator which I use their notation. It's L that goes from the matrix and alpha. So here we have some regularity. Why do we give up C infinity? Now we want to have a nice Banach space. So let's just take matrix of regularity n comma alpha, where n and alpha are big numbers. So we can map this to L infinity of C. So C was a collection of all conjugacy classes in the fundamental group of M.
So n alpha is n with alpha?
Yes.
Alpha is between 0 and 1?
Alpha is between 0 and 1, and you should think about n being very big. N is big as alpha and is 0 and 1, right? Yes. Alpha is between 0 and 1. This is to make a sort of a nice Banach space, and n is big.
And it is important that you have an alpha, that the alpha Cn is not enough for technical reason, you need some alpha.
Yeah, elliptic theory doesn't really work. Elliptic theory only works on Hölder spaces. So you really have to look at the alpha. So of course you can sort of take higher ends and so on, but the right setup is this. So we have this space, this function here from the matrix into L infinity of C, and this is defined by a normalization process where you should think about it. We replace a function itself by somehow the normalized function normalized at the metric G0. So L of G is going to be the following. LG applied to C is going to be the length of C with respect to the metric G divided over by the length of G0 with respect to C. And of course you discard the trivial conjugacy class. That is a beautifully defined function. And so L now, and this is why I want to have this one, L is a function between Banach spaces. So, meaning this is a Banach space, so that's actually linear, it's a convex subset of a linear space. So it's a subset of a Banach space. So that sits in, that's a Banach space here, it's a space of L infinity function with an L infinity norm, and it's differentiable. And now we can compute the differential, and this is actually very explicit. So the differential at the point G0, that's where we are interested in. Now we plug in a tangent vector to the space of metrics. This is now just a section of the space S2 T star M. And what we get out of this is now a relatively simple computation. We get now L2 times LG0 of C, okay, I forgot the C here, sorry, times the integral over from 0 to LG0 of C. And now we just apply in the H of gamma C prime of T, and it's gamma C of T at gamma C prime of T, gamma C prime of T, dt. So meaning this is really the function pi f that I alluded to before. You should think about it now. You have this two tensor. You make out of it on a function, out of it a function that acts on vectors. So in this form here, and now you integrate the result over the periodic orbit. So it's exactly in alignment of what we had before, except that this we think of it as now as being given the interpretation of the differential of L in the direction of this tangent section H. Now here's a main theorem which is due to the main technical theorem of Giacomo and Lefebvre. And now I need to bring this blackboard up. And I see that I made a mistake here. Sorry for this. Main technical result, which I'm going to explain what it means, is the following, and this uses microlocal analysis. And I will then spend the rest of the talk explaining how you set up this microlocal analysis and what is the input that gets you going in the program of looking at the first order differential operator, and somehow think about it as it would be as nice as an elliptic second order operator that could split your space into the one that you can control and the one that you want to understand. The main technical result is, and this is a little bit technical, but I will state it. We take now n bigger than 3n over 2. So n is the dimension of the manifold plus 8. So that's a technical condition here. So we take s bigger than 0 small, and there exists an epsilon bigger than 0, and a big constant c bigger than 0, such that the following holds true. Now if g minus g0, and now in the Cn norm of n, again, we don't need the alpha here, we needed the alpha to set up this nice Banach manifold, is less than epsilon, then there exists a phi in the diffeomorphism of group of M isotopic to the identity, close to the identity, such that the following holds true. So we look at phi star g minus g naught. So in other words, we bring the metric into the best position that we can, thinking about the slice theorem. So we normalize it. We now want to have the metric in the slice of divergence-free tensors. Divergence-free for the metric G0. And now we take a norm here, and this norm is the following. It's -1 minus s, and this is now a Sobolev space. S is positive here, so this is a negative exponent. And we take the Sobolev space of sections of this bundle S2 of symmetric two tensors over the manifold. And this norm here is less or equal than the norm G minus G0. Now comes some technical. The nu is, as before, coming from the Nosov decomposition with some technical normalization constant. Here we have a Cn norm, so that is really a Cn norm. That is a weak norm. That's a norm on a Sobolev space. But now the main point here is on the right-hand side comes the Lg minus 1, and this is the function which is equal to 1 on C. So that is a function that maps every element point in C, which is a conjugacy class in the fundamental group to 1, corresponding to exactly the spectrum, the length spectrum that we get from C naught, G naught by the definition of the map L. And so that is the L infinity norm. And here's some exponent 1 minus nu over 2. You see that immediately this implies the result, the first theorem that I stated. Why? Because if you have L such that Lg is equal to 1, meaning that we have exactly the same marked length spectrum, then this guy vanishes, right? And this says, okay, phi star g, so we have put g into normal position, phi star g normalized to be in the section minus g. Now we have here a Sobolev norm, but these are smooth, so we look at smooth metrics. This is a Sobolev norm. If this Sobolev norm vanishes and we have smooth sections here, phi star g is equal to g naught. So that gives you the result. And this is somehow uninteresting because you look the space of sections that are of high regularity, and where you can, how far you can go, it tells you this constraint you on the epsilon. So that is exactly what we want. And now, of course, the question is, how can we achieve this? And you can see, you might think, okay, there was this result of Kroger-Charouf-Woodinov, which says that infinitesimally everything looked good. But you might also realize immediately this function L and the Banach space L infinity on the space of conjugacy class is ill-behaved. There is no differential operator here, and we don't really know how to somehow relate this to elliptic theory, anything else they can use analysis on. And so somehow this may come as a surprise as well, the Sobolev space. And here comes the point where the microlocal analysis kicks in. And it kicks in the idea of that you can invert in the space of distributions the operator x. That sounds like a bit crazy because the x is the first order differential operator, which is the generator of the geodesic flow. But what you can do is you can look now at a slightly more picture which uses the dynamics and the fact that you have an Noether flow. So you think about x being the generator of the geodesic flow. It preserves the measure flow on T1m. It preserves the measure, preserves the smooth measure, because it is what's called a contact flow. Let's just believe that this is the case. So we normalize the measure to be of total mass 1. That is not a particularly sort of exciting renormalization. It makes the dynamics going. But the point is now that we can have the following simple identity, right? We take two functions, rho and psi functions, and now you know that if you denote by brackets the L2 inner product, then you have x rho psi is equal to minus rho x psi. And this is just the invariance of the measure under the geodesic flow. So meaning that if you differentiate the inner product of rho and x, then the integral over the manifold gives you 0. And this means that minus ix is a self-adjoint operator acting on our two functions, and the spectrum of this self-adjoint operator on R2 of minus ix is contained in the reals. Now, we are almost done with understanding how the setup is going to go. Now we look at this operator. Now we maybe want to look at the operator itself without the minus I, so that is geared at doing a renormalization, where we just renormalize by multiplying everything with some complex number to get the correct setup that allows us to analyze what's going on here in terms of microlocal analysis. So what we have here is that, that for the real part of lambda, we take a complex number, so that the real part of lambda, what lambda is a complex number, is bigger than 0. The resolvents are minus of lambda is equal to minus x minus lambda minus 1. So why can you invert this? Simply because, as you can see, the spectrum of this operator minus ix lies in the reals. So if you put here, if you multiply everything with I, and then you look at the spectrum of x, so here the spectrum of x should be in the complex in the imaginary parts. And now if you have a real part of lambda bigger than 0, you can expect that x minus lambda is actually invertible. Purely formal somehow. And now we take r plus of lambda, which is equal to minus x plus lambda minus 1. So these are well defined. And we can write them down explicitly. So that's an important formula, which you can just work out. R plus lambda of f. So what is this? This is now equal to the integral of 0 to infinity e to the power minus lambda t f of phi t. I should here plug in a point where I evaluate. So I take a function here. I look at the result and apply it to the function. Let's suppose the function is smooth, so that I don't get into trouble. So I get here this integral dt, and I have here r minus of lambda of f at the point y is equal to 0 minus infinity to 0 e to the power lambda t f of phi t v dt. So in other words, so I multiply here, I have this multiply e to the power minus lambda t, the real part is supposed to be positive. Now this is sort of going to, of course, going to 0 if t goes to infinity, this multiplier here. Then I integrate forward with respect to the geodesic flow, and I get this expression if the function f is smooth and hence bounded via on a compact manifold. This is going to exist, and it's going to be easy or relatively easy to understand. Here we have the resolvent for r minus of lambda, which has an expression like this, going forward and backward in the flow. So exchanging the direction of the flow. And now what is the idea that depends analytically on lambda? That is also not hard to see. I mean, you just plug in, you differentiate in direction of lambda. So what is the idea now? The idea is to meromorphic extend this expression here, looking at it as operators acting on suitably defined function spaces. And the point is, of course, which function spaces we are going to take, which is a priori unclear. But so we try to understand nice function spaces where we can meromorphically extend these, looking at these as operators acting on the function spaces to lambda is equal to 0. Say meromorphic extend really on some sort of domain which contains a lambda is equal to 0, and try to understand what the singularities are. And there's a result which is due to 4 and this strand. I'm not sure how to correct all this. And it says the following. So for s bigger than 0, r less than 0, there exist nice Hilbert spaces for which this extension here makes sense. Hilbert spaces meaning you should think about this as Hilbert spaces of distributions which are controlled in some sense. And so what are these Hilbert spaces? There exist, we call it Rs, R, S. So R is less than 0, S is bigger than 0, such that minus X. So that is a subspace of a space of distributions on the unit tangent bundle of the manifold. Minus X defines a maximal unbounded operator on these spaces. And furthermore, so now we have to control the spaces. So this by itself may just be abstract nonsense, but actually it isn't, because we have a lot of information on these spaces. And what is the information that we have? Oops. The spaces, the information that we have is that the superleft space HS of T1M, so these are, this is superleft space of functions, or say, functions, say, of regularity S. S is a positive number, so we can talk about functions. This is contained in this HRS, and this is contained in HR, so now R is negative. And this is a space of distributions. So this is a nice space which we can control. This is a space of distributions where we don't know so much about it. And the point is that this space here, this Hilbert space, lies in between. And so, furthermore, if the real part of lambda is now bigger than minus c comes a number, that's just formal. So the absolute value of R and S, so that is a kind of a formal consideration. Then minus x minus lambda is contained in the domain of x. So that goes from the domain of this minus x minus lambda intersected with the space of this Hilbert space into this Hilbert space. In other words, so you intersect the domain of x minus lambda with this Hilbert space, you end up in this Hilbert space, and it's an unbounded Fredholm operator. Of index 0. And now, so once you have this, then you can study here what happens if lambda goes to 0. You see here, the real part of lambda is bigger than something that is negative. So you're all good. So now in the space HRS, you fix R and S, supposed to be sufficiently small. Smallest here depends on the properties of the geodesic flow. You fix this R and S, you look at this Hilbert space here, you let lambda go to 0, and you study what happens here. And the pertinent result is, and then I stop, this is the last thing I like to say, and this is what is sort of the heart of the argument in some sense of Guillermo and Lefebvre. So which is a result that was proved by Guillermo in 2017, or say published in 2017, which is the heart of the micro-local analysis that goes into the proof of this beautiful theorem. Namely that you can actually understand this meromorphic extension in certain sense very explicitly. And this is exactly what leads to the main technical result, with some, of course, sort of clever, very clever, and deep ramification leads to the main technical result in the paper. And so the point is, and this is the last I'd like to say, so you can meromorphically extend with Guillermo, extend meromorphically, extend these operators are plus lambda or minus lambda acting on these spaces. These spaces H are S meromorphically to lambda, say to a subset of complex plane, to the subset of the complex plane that is cut out by this part of lambda, and understand that lambda is equal to 0 is the only pole on the imaginary axis. And you can understand the second term in the Laurent expansion. To analyze the action of X. This was set up in the initial infinitesimal result of Krog and Sharafutinov. So once you have this, then you get a program that you need to implement. So you're by far not done once you have understood this, but you can implement this program, and using more clever tools for microlocal analysis, you can then get the norm estimate that we are aimed at, which a priori was very ill-posed, because again, on the target, you had this operator L, which goes to L infinity of some countable set that is a priori pretty bad sort of Banach space. It's a Banach space, but a priori pretty bad one. And then the point is somehow to relate this operator L to norms that you get on Sobolev spaces using tools for microlocal analysis. So thank you for your attention.
Thank you. Are there questions? So the X-ray transform, was this curly L?
Yes.
Yes. And why is it called like this?
I don't know. Maybe Vivian knows. I don't know why it's called X-ray transform. I was wondering the same thing.
Okay, if I may ask a very sort of general
Sure.
question, because I know the microlocal theory originally came from a sort of a sheet theoretic algebraic perspective with the Tato school. So and also I know that this sort of algebraic theory has been used in the symplectic geometry a lot. So I'm just wondering why now we are doing microlocal analysis without any sort of theory perspective, where it hasn't been useful.
No, the microlocal analysis really comes from looking at the Annosa flow. So you have this Annosa flow. This is why I was sort of pondering on the point that you have an Annosa flow here. And the microlocal part in the analysis really consists in decomposing functions and distribution spaces into subspaces which you can study using the dynamics of the flow. And so that is somehow, this is at the end of the day used to construct, for example, this whole space that I was talking about, which was constructed by Foer and Söstrand. But this is really the microlocal part in the analysis really comes from somehow, again, using wavefront sets for differential operators and setting up the corresponding Hilbert spaces. It's a really sort of clever, I would say, very clever theory. And of course, I mean, this was highly developed during the last 20 years. And again, as I try to stress, 20 years ago, people were trying to prove the same result, and it didn't go anywhere, and the tools were not there.
In the Foer and Söstrand statement, which is still on the board, what's the point of having an unbounded operator? I don't see it in your argument.
The point is that the operator, it's a maximal operator. It's unbounded, though that's, of course, some bad news. But it's a maximally defined operator. And this means that somehow the point is that you can analyze it for all lambda. And this allows you, so you have the same Hilbert space where you can apply the operator on, or let the operator on work for all lambda. And this allows you to somehow meromorphic extend in the space of operators. So it's not a meromorphic extension in the space of functions, it's a meromorphic extension in the space of operators, which is a little more delicate if you want. Sorry?
How do you obtain the isotopy at the end?
Oh, you see the isotopy, I just copied it from the statement, but the isotopy here has no meaning because we put it up in the setup. We look at divergence-free sections. So the isotopy that you get is, so if you think about it, so here you get a decomposition of your space of two tensors, right, to those which are divergence free for the initial metric, and those that are sort of complementary to divergence free, and those that are tangent to the tensors coming from the diffeomorphism group, as I tried to explain. And so in some sense, so you somehow define it away. The isotopy, in a certain sense, again, has no meaning because you did already analyze it when you looked at image of the operator del star, which is transverse to the kernel of the operator D, so divergence-free operators. That is sort of some sort of formal, everything is local. Somehow, again, so the isotopy is hidden in the fact that you look at the image of the del star, and so there was a formula which is still on the board. Del star alpha is equal to minus 1/2 the Lie derivative of G naught in respect to alpha star. And so in other words, everything that is in the image of the del star, it gives you the isotopy automatically because it gives you a flow in the space of metrics. Does this make sense? And so somehow at the end it doesn't play any role anymore. You need to analyze what's going on before you even start, because you have to get rid of the diffeomorphism group in some way. And that's the way to do it. Slice theorems by themselves are not super innovative. They have been used in many different contexts, quite often. So that is not the main innovation of the work. That the main innovation of the work is sort of what I tried to explain at the end.
I think we can thank Ursula again.
Thank you.
Et elle va nous parler de Finite Tab Blow-up for the compressible fluids and for the energy supercritical defocusing non-linear Schrödinger equation.
Merci. Donc c'est un grand plaisir d'être là et présenter une série de résultats de Franck Merle, Pierre-Raphaël Igradnianski et Jérémy Tseftel qui concernent l'explosion en temps fini pour deux modèles qui sont en apparence sont très différentes et donc ils sont d'origine différente et de nature différente, mais toutefois on va voir qu'ils sont liés et en particulier ils ont un régime d'explosion en gamma qui était découvert par Franck, Pierre, Igor et Jérémy et dont je vais parler. Donc il s'agit d'une part l'équation de Navier-Stokes compressible et d'autre part l'équation de Schrödinger non linéaire défocalisant à énergie surcritique. Et donc là, je vais commencer par présenter un peu les équations qu'on va regarder. Et je commence par les équations des fluides compressibles, donc l'évolution d'un fluide compressible avec les viscosités, et décrit par les équations de Navier-Stokes qui sont là. Donc ici, V, c'est la vitesse de le fluide. Rho, c'est la densité qui est supposée être positive. Il y a deux coefficients de viscosité. Bon, je ne note pas mu prime. Là, ce n'est pas tout à fait physique ce que j'ai écrit, mais donc, du point de vue technique, c'est mieux. Et puis, il y a la pression P qu'on va supposer être uniquement une fonction de rho. Cette fonction est là. Et on va considérer les solutions qui tendent vers 0 à l'infini, voilà, avec cette condition, en gardant la densité positive. Je vais peut-être recopier ce système au tableau pour le voir sous les yeux, si je trouve la clé. Voilà. Donc on a une équation pour ρ dθ plus la divergence ρv égale 0. Une équation pour V qui dit que ρ fois dTv plus ρ V produit scalaire avec le gradient appliqué à V plus le gradient de la pression qui dépend de ρ égale mu remplacé en V plus mu prime gradient de la divergence de V. Et donc, la pression est donnée par la loi qui est là. Au gamma moins 1 sur gamma, c'est juste une constante qui est commode. Et puis, il y a rho la puissance gamma, et gamma est supposée être plus grande que 1. Donc, ce serait la question de Navier-Stokes qu'on va regarder. Donc, si on regarde les limites mu et mu prime tend vers 0, bah, on récupère l'équation de Navier-Stokes qui sont en haut. Toujours avec les conditions initiales qu'on suppose être décroissantes à l'infini et avec la densité strictement positive. Bon, dans le cas de l'équation d'Euler, le fait qu'on va regarder les solutions qui tendent vers 0 à l'infini est un peu moins important parce qu'elle a une vitesse de propagation finie, donc on peut toujours les localiser. Donc là, si on regarde les équations, on constate tout de suite qu'il y a deux lois de conservation évidentes, la conservation de la masse qui est là, et ensuite la conservation du moment. Et puis on a pour les deux, en fait, pour Navier-Stokes et pour Euler, et puis on a aussi l'égalité qui exprime la balance d'énergie, qui devient une loi de conservation dans le cas d'Euler et qui, voilà, juste cette relation-là dans le cas de Navier-Stokes. Bien. Donc, une fois, si on regarde les équations d'évolution, donc la première question qu'on se pose, c'est est-ce que le problème de Cauchy est bien posé? Mais avant, je vais parler de Schelling, excusez-moi. Donc, les équations Euler qu'on obtient ici en prenant mu et mu prime égale 0, et invariant par rapport à une famille de transformations d'échelle à 2 paramètres. Donc il y a lambda qui est positif et R qui est arbitraire. Donc maintenant, si on regarde Navier-Stokes, une seule invariance de cette famille à 2 paramètres sur V, c'est l'invariance qui correspond à une valeur précise de R qui est 2 gamma sur gamma plus 1. Donc le scaling serait important pour nous. En fait, c'est toujours important. Maintenant, concernant les questions d'existence locale, donc pour Navier-Stokes compressible, c'est surtout le cas où la densité est strictement positive et séparée des zéros par une constante qui a été étudiée. Et donc ça sont des travaux très classiques. Mais maintenant, ce n'est pas notre cas. Notre cas, donc la densité est envers 0 à l'infini. Et donc ce cas-là a été étudié dans les travaux qui sont marqués dans ce théorème par Cho et Kim. Dans le cas plus général, en fait, ils supposent que la densité est supérieure ou égale 0. Et ils ont identifié une condition de compatibilité qui, vous voyez, apparaître dans le théorème. C'est 0 la puissance moins demi. Et puis cette expression qui vient de ce terme-là, il faut que ce soit dans L2. Donc sous cette condition-là, on a quand même une bonne notion d'existence locale pour des données qui sont ρ0 dans H1 intersecte avec W en 6, ce sont des espaces de Sobolev, et V0 est dans H1 poids, c'est l'espace de Sobolev homogène, et H2 aussi avec le poids homogène. Et on a aussi un critère d'explosion, donc c'est-à-dire que soit la solution est globale, soit les normes qui sont là tendent vers l'infini quand on approche le taux d'existence maximale. Il faut dire aussi qu'il existe toute une théorie des solutions faibles introduites par Lyons. Ces solutions faibles sont globales, mais on n'a pas d'unicité. En fait, et ces solutions ne vérifient pas en général le balance d'énergie. En fait, elle est juste une inégalité. Donc, ce n'est pas des solutions là que je vais regarder. Donc, nous, on va regarder des solutions fortes, quelque sorte de vraies solutions. Là, donc ça, c'est Navier-Stokes. Maintenant, donc, si on passe à l'équation de l'air, donc ça devient encore plus simple. Donc, il est bien connu depuis les travaux qui sont là que, en fait, l'équation de l'air compressible est un système hyperbolique symétrisable. Et donc, entre dans la théorie tout à fait classique qui dit qu'on a une existence, une unité de solution dans l'espace HS dès que S est strictement plus grand que D sur 2 plus 1, et D c'est l'émotion. Voilà, avec le critère d'explosion qui est ici aussi. Donc, je dois dire aussi que les résultats que je cite ne sont pas du tout optimaux, mais donc c'est suffisant pour ce dont je vais parler. Ce sont des résultats classiques. Depuis, il y avait énormément de progrès dans les espaces plus sophistiqués. Mais pour nous, ce serait plus que suffisant. Bien, donc maintenant, je vais passer à le deuxième modèle dont je vais parler, qui est l'équation de Schrödinger non linéaire défocalisant. Donc, elle est là, en haut, ici. Et donc, défocalisant, ça veut dire que je le signe plus devant le terme non linéaire. Donc, si on a le signe moins, on dit que c'est focalisant. Donc, pour cette équation, on a deux lois de conservation qui sont là. La masse, la conservation de la masse, du moment et d'énergie. Et donc, comme l'équation de Navier-Stokes est là, on a aussi un scaling qui préserve l'équation, qui est ici. Je vais peut-être quand même écrire l'équation ici de Schrödinger non linéaire. Bien, et donc si on regarde... Pardon? Oh, pardon, ouais. Merci. Donc ce scaling préserve aussi la norme de Sobolev qui est ici. je sais pas, donc ça doit être S critique, en fait, c'est pas SP, c'est SC. Voilà, et donc maintenant, si on compare ce norme critique avec la norme d'énergie qui fait intervenir la norme H1, on peut classifier l'équation comme étant énergie sous-critique si ce S critique est strictement plus petit que 1, critique si ce S critique égale à 1, et énergie surcritique si c'est le plus grand, strictement plus grand que 1. Et ça aussi correspond à, avec cette classification, on peut le voir aussi au niveau de la conservation d'énergie. Donc si je reviens, il y a deux termes. Le premier terme, donc les deux sont avec le signe plus, c'est très important. Donc le premier terme, c'est l'énergie cinétique, le deuxième, c'est l'énergie potentielle. Et on constate que dans le cas énergie sous-critique, l'énergie cinétique avec la masse contrôle l'énergie potentielle. Et donc ce n'est plus le cas donc, si on est surcritique. Bien, maintenant, concernant l'existence locale, pour le problème des cachis, bon, c'est une question qui est extrêmement bien comprise. On sait que la théorie locale est contrôlée en fait par le scaling, au sens que le problème des cachis avec les conditions initiales dans HS est localement bien basé dès que S est plus grand que 0 si l'expression critique est négative est plus grand que supérieur ou égal à S critique si c'est positif. Et en plus, si S est strictement plus grand que S critique, alors le temps de vie des solutions dépend uniquement de la norme S de données initiales, ce qui de façon classique signifie que soit les solutions sont globales, soit sa norme HS tend vers l'infini quand T est inverté. Puis je notais quelques noms qui ont marqué en fait, le développement de théories locales. Donc, en fait, ça remonte aux travaux de génie Brevelo, et puis le truc critique, c'était fait par Cazenave et Weissler. Maintenant, donc là, je suis prête à expliquer le lien entre deux modèles. Ce lien, en fait, est assez bien connu. Et donc, il s'agit de la formulation hydrodynamique de l'équation de Schrödinger non linéaire, qui est donnée par la transformation des modules 1 qui est là. Donc, pour les solutions qui ne s'annulent pas, on les écrit sous la forme une amplitude fois une phase. Et il s'avère que donc, si on prend la racine carrée de l'amplitude et si on prend le gradient de la phase, on se retrouve avec un système qui ressemble énormément à l'équation de l'air compressible, perturbé par un terme qu'on appelle le terme de pression quantique, qui est à droite. Alors, donc, la seule différence par rapport à l'air ou Navier-Stokes qui est là, c'est un demi avant les dérivés qui sont là. C'est juste, on peut l'enlever en changeant le tome, on le fera dans quelques instants. Voilà, donc là, cette observation est très, très, très vieille. Elle était utilisée dans pas mal de contextes. D'abord pour étudier l'équation de Schrödinger non linéaire, par exemple dans les constructions de type optique géométrique, et aussi pour étudier, donc, qui était après appliqué à l'étude des caractères mal posés ou de croissance de normes. Donc là, la liste des travaux que je donne ici, ce n'est pas du tout complet, mais c'est juste des exemples. Cette relation entre l'équation de Schrödinger non linéaire et l'air compressible était aussi utilisée dans l'autre sens pour étudier des équations de mécanique de fluide. Bon, là, je ne vais pas donner de citation, mais ça existe. Bien. Donc voilà, deux modèles qui vont nous intéresser, ils sont liés par cette formulation hydrodynamique de l'équation de Schrödinger non linéaire. Donc maintenant, les questions qui vont nous intéresser, c'est les questions d'explosion en temps fini. Donc dès qu'on a compris plus ou moins le problème des cachis locaux, les questions suivantes qui se posent, c'est de savoir est-ce qu'en réalité les solutions sont globales ou on a l'explosion en temps fini. Je vais d'abord raconter un peu l'histoire pour Schrödinger non linéaire, parce qu'on a juste en parlé. Donc déjà, si on regarde le cas à énergie sous-critique, donc là tout est simple, puisque en fait, dans ce cas-là, la norme H, si on se place dans H1, la norme H1 est contrôlée par la loi de conservation, puisque nous sommes dans le cas défocalisant, et du coup ça implique immédiatement l'existence globale. Il s'avère que dans le cas à énergie critique, c'est-à-dire le coefficient critique égale 1, on a également l'existence globale, mais ça devient beaucoup moins trivial de le montrer. En fait, c'était fait, mais avec beaucoup d'efforts et dans une longue série de travaux, en commençant par les travaux de Bourgon et Griolakis en dimension 3 et 4, et pour des données réelles. Ensuite, en étape important, était franchi dans le travail de Keleander, Kiel, Stefila, Takaoka et Tao, qui ont montré en fait l'existence globale en dimension 3 pour NLS énergie critique pour des données en fait, pas nécessairement radiales, donc pour des données générales. Et puis donc c'était généralisé au cas de dimensions plus grandes par Rickman et Visson tout seul. Donc concernant maintenant le cas énergie surcritique, donc S critique est plus grand que 1, et donc là il y a une faute de frappe, c'est P plus grand que 2 sur D moins 2. Et donc en particulier dimension est plus grande que 3. Donc les questions restaient complètement ouvertes longtemps. En fait, il n'était même pas clair qu'est-ce qui se passe parce que les gens avaient une tendance de penser que l'existence globale persiste. D'une part parce qu'il y avait des simulations numériques qui semblaient le confirmer. D'autre part parce que tous les régimes d'explosion qu'on sait dans le cas focalisant, dans le cas focalisant, l'explosion arrive dès que l'explosion critique est plus grande que 0. Tous ces régimes qu'on connaissait étaient liés d'une ou d'autre part à l'existence de solitons ou de solutions autosimilaires appropriées. Et je pense que c'est de cela qu'Anne-Sophie a parlé hier. Et donc, tous ces objets-là n'existent plus dans le cas des focalisants. Donc là, c'était l'argument pour dire plutôt qu'en fait, pour penser qu'il n'a pas d'explosion, mais d'autre part, donc il y avait Tao qui construit des exemples des systèmes, des équations de Schrödinger non linéaires, défocalisants, pour lesquelles donc, elle a montré que, qu'il y a l'explosion en temps fini. Et donc voilà, le résultat décisif était obtenu par Frank Merle, Pierre-Raphaël Igaragnanski et Seftel, qui ont construit des solutions qui explosent en temps fini pour NLS à énergie surcritique qui est là, en dimension de 5 à 9, et pour certains choix de non-linéarité, donc de P. Et ça, ils ont fait ça en passant par les formulations hydrodynamiques de l'équation de Schrödinger que j'ai montré tout à l'heure. Et en fait, c'est de ça que je vais parler, mais avant, je vais revenir à l'équation de Navier-Stokes compressible et DLR et aussi dire quelques mots de ce qu'on connaissait avant sur l'explosion pour ce modèle. Voilà, donc là, je me place tout de suite dans le cas de D supérieur ou égal à 2, parce que D égale à 1, c'est un monde à part. Pour l'air très bien étudié, donc les résultats en fait, remontent aux travaux de Riemann. Donc là, je reste dans le cadre multidimensionnel. Donc, dans le cas multidimensionnel, le fait que les solutions issues de données initiales de classe C infinie, qui en plus sont des perturbations à support compact de l'état stationnaire, et il peut être arbitrairement petit dans ce sens-là, est connu depuis les travaux de Sideris. Pour Navier-Stokes, c'est un peu plus récent. Donc, il y a un travail de Azanova qui montre explosion en temps fini, en dimension supérieure égale 3 et sur certaines conditions sur gamma, qui est là. Donc gamma plus grande que 2D sur D plus 2. Mais donc ces travaux, en fait, procèdent utilisent l'argument des contradictions basées sur certaines considérations de convexité. Et donc, il ne donne aucune information sur la nature de la singularité qui se développe. Donc, juste que voilà, la solution ne peut pas exister pour tout T. Mais il disait sur ce qui se passe et pourquoi ça n'existe pas. Pour LR, il existe en fait la singularité typique, c'est un choc. Un choc, ça veut dire que les solutions restent bornées, donc les densités et les vitesses restent bornées, mais leur dérivé premier explose. Et donc, il existe une littérature absolument énorme sur les formations de chocs pour l'équation d'L compressible. Je pense que les premiers travaux sont dus à l'ENAC, qui a étudié, pas nécessairement LR, mais elle a étudié des équations hyperboliques, des équations du type d'onde quasi-linéaire assez générales. Et elle a montré que si l'équation ne vérifie la condition nulle de Kronecker-Mann, alors il y a l'explosion, et même pour des données arbitrairement petits à support compact. Et donc, génériquement, elle décrit quel type qu'est-ce qui se passe, comment se forme le choc. Donc là, bien qu'elle a, donc pour les données qu'elle a considérées, elle avait une description assez précise de la singularité. C'était juste la description de la première singularité, parce qu'on peut se poser une question plus générale du développement maximal des données initiales. Et donc ça, ce problème a été étudié par Christodoulou dans le cadre des équations de l'ère relativiste et ensuite par Christodoulou-Miao. Et depuis, donc, il y avait d'autres progrès dans cette direction-là. Donc là, je ne vais pas vraiment donner des détails, mais donc ça reste une activité très intense. Donc il y a énormément de résultats qui sortent sur les formations de chocs. Mais le choc, ce n'est pas la seule possibilité, ce n'est pas la seule singularité possible qui peut se développer dans l'équation d'Euler compressible. On peut avoir aussi des singularités plus fortes pour lesquelles à la fois, pour lesquelles la densité et les vitesses explosent eux-mêmes. Et donc l'exemple en fait de cette singularité, on peut obtenir en regardant les solutions autosimilaires pour LR qui sont connues depuis les travaux de Güderley et Sidov. Donc ce sont des solutions radiales, au sens que donc, le profil grande R est radial et la vitesse, en fait, c'est le gradient d'une fonction radiale. Donc si on met ça dans l'équation de LR, donc on trouve un système pour les profils qu'on peut résoudre, mais en général, ces solutions, soit ils ne sont pas globales, soit ils ne sont pas C infini. Et en fait, donc le point, en quelque sorte, le point de départ des travaux de Merle, Raphaël Radnjansky, etc., sur l'explosion pour un LS défocalisant et pour Navier-Stokes compressible. Et ces solutions-là, mais sauf que donc, eux, ils avaient besoin de solutions de classe C infini pour faire marcher leur analyse. Et ils ont effectivement montré que de tels objets existent. Et puis qu'on peut les utiliser pour produire des solutions explosives pour les deux modèles qu'on va regarder, pour Schrödinger non linéaire et pour Navier-Stokes compressible. Voilà, donc c'est ça ce que je vais expliquer dans cet exposé. Mais donc le plan serait suivant. Tout d'abord, je vais réécrire les deux modèles en coordonnées autosimilaires qui viennent de l'équation d'Euler qui est essentiellement là. Voilà, en coordonnées autosimilaires eulériennes, ce qui fait apparaître ce régime donc eulérien explicitement dans les équations. Ensuite, je décrirai les résultats d'existence de solutions de classe C infini, de ce type-là pour LR. Ensuite, avec ça, je pourrais formuler les résultats d'explosion pour Schrödinger et pour Navier-Stokes. Et ensuite, s'il me reste le temps, j'espère qu'il me restera un peu de temps, je dirai quelques mots sur les démonstrations. Bien. Voilà. Donc je commence, donc je reprends l'équation de Navier-Stokes qui est là. Et donc on va faire quelques modifications. Tout d'abord, il est commode de changer le ton, de passer de t à t sur 2 pour avoir le même truc pour Navier-Stokes et pour Schrödinger. Puis il serait commode aussi de travailler plutôt avec la racine carrée de la densité qu'avec les densités elles-mêmes. Donc pour ça, j'écris ρ comme ρ carré, en fait ρ rond de carré, et je mets un petit coefficient de normalisation, ce qui n'est pas grave. Ensuite, en fait, les solutions, je vais me limiter aux solutions qui sont radiales, et donc ce qui permet d'écrire la vitesse comme le gradient d'une fonction phi, qui serait une fonction radiale. Et donc ce phi, on peut fixer une constante près par relation qui est là. Et je note par P gamma moins 1. Gamma est là-bas dans la pression. Et puis, donc, dans ce nouveau ρ, dans ce phi, on fait le changement de variables autosimilaires. Donc, on passe de variable x de l'espace à la variable y qui est là. Donc x multiplié par lambda de t. Et ce lambda, en fait, il est ici. Si on veut le voir explicitement en termes de t, il est ici. Donc ça correspond exactement aux solutions autosimilaires qu'on a vu juste avant. Et puis on introduit aussi le nouveau ton, taux, qui est donc logarithmique par rapport au ton initial. Et grand T qui figure là, ce serait notre ton d'explosion. Voilà, et donc ces objets-là aussi vérifient les équations qui sont écrites. Bien, donc si on le fait, alors on se retrouve avec le système qui est ici. Donc là, il y a deux équations. La première est pour la densité, donc pour grande R. Et la deuxième pour la phase. Donc ici, grande lambda, c'est l'opérateur c'est le générateur de dérotation. Et puis à droite, donc le reste est clair. Et à droite, donc on a la contribution en rouge, c'est les contributions de termes viscosité qui sont là. Quand on l'a écrit dans ce nouveau coordonnées. Et donc, on constate que donc, il y a un facteur, B carré Navier-Stokes, qui est de la forme exponentielle moins epsilon Navier-Stokes fois tau, avec epsilon Navier-Stokes qui est là. Donc, dedans, il y a un paramètre R, c'est le paramètre de notre changement autosimilaire. Parce que dans les coordonnées autosimilaires des rayons, donc il y a ce paramètre. Donc on a une famille, je rappelle, une famille de scaling à deux paramètres. Et donc on constate que si ce R est plus grand que 2 gamma sur gamma plus 1, ça c'est exactement le scaling de Navier-Stokes. Alors ce epsilon à Navier-Stokes est positif, et donc le terme de viscosité est envers 0 quand tout envers l'infini. Donc ce qui montre que dans ce régime-là, la dynamique de l'équation de l'air devient dominante dans la dynamique de Navier-Stokes, près de poids singulier, donc grand T, qui en termes de nos tons correspond à taux envers plus infini. Bien. Donc maintenant, on va faire la même chose avec Schrödinger. Donc on prend la formulation hydrodynamique. Donc on suppose que la solution n'y s'annule pas. On l'écrit comme une amplitude et une phase. Et dans l'amplitude de la phase, on fait le changement de variable. Donc pour aller, on fait le changement de variable autosimilaire comme tout juste avant. Voilà, et donc ça donne le système exactement de la même forme, sauf que le terme en rouge a une expression différente, mais il y a quand même un B carré avant qui s'écrit comme exponentielle moins epsilon s tau. Avec epsilon s maintenant c'est R moins 2. Donc là, de nouveau, voilà, donc si R est plus grand que 2, on constate que la dynamique de Schrödinger va être dominée par les dynamiques de R dans la limite taux envers plus infini, exactement comme avant on a vu pour Navier-Stokes. Donc en fait, deux modèles prennent la même forme. Ils font apparaître comme régime dominant la dynamique de R. Et c'est ce qu'on va utiliser. Bien, donc du coup, si on arrive pour l'équation de Euler qui est là, voilà, donc là aussi je vais écrire l'équation de Euler dans les coordonnées autosimilaires, parce que c'est important. D taux R plus R-1 sur P plus lambda R égale 2 plus 2 grade phi grade R plus R option phi égale 0 D taux phi plus R mod 2 plus lambda phi plus grade phi au carré plus R puissance de P égale 0. Donc, imaginons maintenant qu'on a des solutions stationnaires pour ce système de Euler. Alors, si on arrive montrer qu'elles sont stables par rapport aux perturbations qui apparaissent dans les Stokes et dans les Schrödinger non linéaires, donc ça voudrait dire qu'on a des solutions globales pour nos deux modèles, globales par rapport au ton autosimilaire taux, qui restent proches des solutions stationnaires de Euler, qui en fait, ce sont des solutions autosimilaires dans les variables originales, donc ça nous donnera les résultats d'explosion. Donc la première question, c'est d'étudier, de savoir s'il y a des solutions convenables stationnaires pour ce truc-là, et est-ce que donc ils ont des propriétés de stabilité qui permettront ensuite de s'adapter aux deux modèles qui nous intéressent. Voilà, donc on va commencer par regarder les équations pour les solutions stationnaires, donc autrement dit pour les solutions autosimilaires. Donc on constate immédiatement, en regardant juste la tête des équations, que donc là je normalise par la condition qu'en 0 les densités vont 1. Et puis on s'intéresse aux solutions radiales. Et donc on constate immédiatement qu'il existe une unique solution radiale de classe infinie définie près de l'origine pour y petit. Et puis à l'infini aussi, donc si on peut construire des solutions, en fait une famille à deux paramètres de solutions qui sont engendrées par les solutions linéaires, c'est-à-dire je prends juste cette partie, donc il n'y a pas de taux ici. Donc on regarde juste ça, ça donne quelque chose de croissant et donc on peut le monter pour avoir les solutions non linéaires. Et donc la question, est-ce que la solution qui vit près de l'origine en fait est globale et à l'infini en fait arrive dans cette famille à deux paramètres. Donc pour le répondre, donc, là, qu'est-ce que c'est? Puisqu'on se limite aux solutions idéales, c'est juste un système de deux quadifs, mais qui ne sont pas autonomes. Il s'avère qu'il y a une transformation que le transforme ce système en système autonome, et je vais montrer ça. Voilà, donc si on fait ce changement de variable qui est là-haut, donc, au lieu de travailler avec grand R, on va travailler avec sigma. Et phi, donc, de phi, on passe à W. Et puis, donc, ce ne serait plus avec R. Donc, on va travailler avec S, qui est logarithme de R. Donc, en ces nouveaux coordonnées, le système pour les solutions stationnaires prend la forme qui est ici, où delta, delta 1 et delta 2 sont deux polynômes explicites qui ne dépend pas de S, donc c'est un système autonome. Donc delta 0 est quadratique, delta 1, delta 2, ce sont des polynômes cubiques, et donc il y a plein de paramètres, mais en réalité, dans le système, il y a trois paramètres. Il y a la dimension, D, il y a non-linéarité, donc c'est gamma pour les Stokes, P pour Schrödinger, donc ils sont liés, P c'est gamma moins 1. Et puis là, on l'écrit sous la forme L qui est 2 sur P ou 2 sur gamma moins 1. Et donc là, il y a ce W indice E qui est donné par cette expression. Je vais faire un petit dessin. Peut-être un... Je vais commencer là. Sigma W. Donc tout à l'heure, je vous avais dit qu'il y a une solution qui vit près de 0, qui est bien. Mais donc 0 en variable S, c'est S envers moins infini. Et dans ce cas-là, si on regarde notre changement de variable, on constate que nécessairement sigma tend vers plus infini. Donc cette solution, c'est quelque chose qui vit ici. Et W tend vers justement la valeur W indice E qui est apparu dans ce système. Et d'autre part, donc, il y a les solutions qui décroît à l'infini. Donc à l'infini par rapport à Y, c'est S. C'est S tend vers plus infini. Et donc les solutions, on veut que les solutions convergent vers 0. Je mets ça pour P0, c'est 0, 0. Donc la question est, est-ce que les solutions qui vivent par là arrivent ici? Il est clair qu'avec, à cause de ce delta 0, donc il y a des zéros de delta 0. Donc là, c'est delta 0 égale 0. Donc ils doivent traverser, ces droites-là. Et les traverser cette droite-là, on peut uniquement quand delta 1 et delta 2 aussi s'annulent. Donc en fait, il y a des poids très importants qui vérifient donc l'équation delta 0, delta 1 égale delta 2 égale 0. Donc les solutions de cette équation dépendent des paramètres. Donc là, on va tout de suite placer dans le cas donc D supérieur égale 2, parce que de toute façon on s'intéresse au cas multidimensionnel. Elle est positive, parce que c'est notre non-linéarité. Et puis, donc, si on suppose que R, ce troisième paramètre de scaling, est plus petit que R étoile, avec R étoile qui donne là, alors donc cette équation qui a une solution triviale qui est là, ça c'est le point P1. Il y a deux autres solutions, P3 et P2. Donc c'est là où la solution qui vit ici peut traverser cette droite pour arriver à l'origine. Donc il y a un autre point important qui est le point que je notais, je crois, par P4. Et en fait, c'est une solution de l'équation delta 1 égale delta 2 égale 0. Ça veut dire que ce sont des poids stationnaires. C'est le poids stationnaire de notre système. Et donc sa position par rapport à cette droite aussi dépend des valeurs de R, comme j'explique quelque part. Donc ce poids va être plus bas que la droite, donc quelque part par là. P4 si R est plus petit que R étoile avec étoile en bas. Et il va monter si, donc ça c'est mon deuxième dessin. Donc ça c'est P1, P0, P3, P2, et donc là ça monte quelque part ici. Donc ça serait P4. Donc ça, ce serait dans le cas R plus grand que R étoile en bas. Il y a ensuite on va restreindre encore plus de paramètres Voilà, donc en supposant que R est entre 1 et R étoile en bas, donc ce que nous sommes là, si L est plus petit que D, et que R est plutôt, donc nous sommes dans cette position-là, si L est plus grande que D. Voilà, donc dans ce cas-là, on peut facilement montrer, en regardant le portrait de la phase, que donc les solutions qu'on sait exister, en fait la solution qui est unique, qui est définie près de 0, en fait arrive en temps fini au point P2. Voilà. Et que d'autre part, il y a des solutions qu'on veut avoir près d'infini, en fait toute une famille de solutions qui arrivent aussi en temps fini en CP2. Bon, là, je ne vais pas trop dessiner parce que je dessinerai la solution finale. Qui arrivent aussi en P2. Et que donc ça donne tout de suite quelque chose qui est continu, qui est infini en dehors des poids, donc S2, donc c'est le moment d'arrivée de cette courbe en P2. Mais en réalité, c'est même mieux, ça a une régularité finie CK qui dépend en fait des valeurs propres de l'équation linéarisée, du système linéarisé au voisinage de ce point P2. Plus précisément, si on regarde la matrice jacobienne de notre système, donc définie par ces deux fonctions delta 1 et delta 2, donc il y a deux valeurs propres, lambda moins lambda plus. Tous les deux sont négatifs dans le régime qu'on regarde, donc le poids est stable. Et donc la régularité qu'on obtient pour les solutions, c'est la partie entière de lambda 1 divisé par lambda plus. Et donc en fait, on a toute une famille de solutions qui ont les propriétés qu'on veut près de 0, ont les propriétés qu'on veut près de l'infini, qui sont de classe CK. Mais il s'avère que cette régularité finie n'est pas suffisante pour pouvoir contrôler la stabilité de ces solutions, la stabilité dont on aura besoin pour traiter ensuite Navier-Stokes et Schrödinger. Donc, la première contribution des auteurs dont je parle, c'était de montrer qu'il y a quand même des ensembles de valeurs de paramètres pour lesquels il y a des solutions C infinies. Donc, plus précisément, ils ont montré le théorème suivant. Voilà. Donc, il existe un ensemble de couples DL que je note par P, tel que pour tout couple dans cet ensemble, il y a une suite de valeurs, de paramètres de scaling à n qui convergent vers les valeurs limites. Donc, j'ai oublié de préciser. Donc, la valeur limite est là, R2 étoile. Donc, si on est dans ce cas-là, notre R2 étoile, c'est celui-là. Et si on est dans le deuxième cas, c'est celle qui est plus grande. C'est R étoile avec étoile en haut. Voilà. Donc, il existe une suite qui converge vers cette valeur limite pour laquelle on a une solution C infini radiale globale qui est décroissante à l'infini avec le comportement qu'on a déjà vu. Et de plus, donc cet ensemble que je ne précise pas, donc il contient les couples suivants. Il contient déjà les couples de la forme 3 à L, c'est-à-dire qu'on prend la dimension D égale 3 et puis L plus ou moins quelconque, positive et différente de 3, parce que je vous rappelle qu'on ne regarde pas L égale D, sauf une suite exceptionnelle de valeurs qui ne peut accumuler que vers 0, 3 et plus infini. Et puis, donc, certains couples particuliers qui sont listés ici. Donc, ce théorème, donc, elle s'obtient avec une analyse extrêmement fine et compliquée dans les limites R tend vers R 2 étoiles qui correspond à l'une des valeurs propres qui tend vers 0, donc lambda plus dans ma notation, et l'autre reste d'ordre 1. Donc, géométriquement, ça veut dire que là, c'est le cas où le point P4 arrive au point P2, et ici, c'est le point P2 et P3 qui se confondent. Et donc, cette analyse, en fait, vraiment, c'est un gros travail, absolument non trivial. Et bien que dans ce régime, vous voyez que la régularité de solution des autres solutions tend vers l'infini, cette régularité quand même reste insuffisante pour faire l'analyse qui suit. Donc, il fallait vraiment aller chercher les solutions C infini et ce n'est pas du tout évident. Parce que pour les distinguer des autres, ça veut dire que dans leur série de Taylor, on doit aller à l'ordre K, avec K qui tend vers l'infini en fait. Okay. Bon, moi je ne vais pas dans les détails, parce que sinon je n'arriverai pas à l'explosion. Déjà, je ne sais pas si je vais arriver. Bien, donc là, c'est l'existence de solutions C infini. Et puis, donc, il y a un autre. Donc, il faut aussi, pour pouvoir assurer que ces solutions sont stables, il faut avoir certaines propriétés de positivité par ces objets. Donc, ça, c'était aussi vérifié par Franck, Pierre, Igor et Jérémy dans certaines. Non, je ne sais pas. Ok, là, je vais aller là. Dans certains régimes de paramètres, donc voilà, donc je vous montrer que si on prend le couple que j'ai noté juste avant, donc 3L avec L comme il faut, donc L évite la suite exceptionnelle, alors si L aussi en plus est plus grande que racine carrée de 3, et aussi pour les couples, voilà, 4 couples spécifiques qu'on va utiliser pour l'équation de Schrödinger non linéaire, on a certaines propriétés de positivité qui sont là données par cette proposition. Et ces propriétés-là, on va utiliser, donc ces propriétés assurent la caressivité de l'opérateur linéarisé correspondant au profil qui était construit. Bien, donc avec ça, je vais formuler les résultats d'explosion quand même. Donc je commence par l'équation de Navier-Stokes. Donc on se place en dimension 3. On met les conditions sur l'équation de viscosité, mu prix supérieur ou égal 0. Ce n'est pas tout à fait physique, en fait, c'est mieux que les conditions physiques, mais ça marche aussi parce que nous sommes dans le cas radial, en fait. Et donc je note par L comme il faut 2 sur gamma moins 1. Alors, en supposant que L est plus grande que racine carrée de 3, et là c'est précisément la condition qui assure la compatibilité de régime de compatibilité de Navier-Stokes avec le régime Eulérien qu'on a vu tout à l'heure sur epsilon Navier-Stokes, il fallait que ce soit positif. Et ça, c'est précisément la condition pour que ce soit positif, au moins pour ce R limite près de laquelle on travaille. Et donc, on suppose que L évite la suite exceptionnelle donnée par le théorème précédent. Alors, pour toute N, on trouve des données initiales de classe H infinie, ça veut dire que dans tous les espaces de Sobolev, qui forment une variété de dimensions finies, de sorte que pour ces données initiales, les solutions de l'équation de Navier-Stokes qui est ici, là, explosent en temps fini, que je note par grand T. L'explosion a lieu à l'origine, et puis donc l'explosion se fait par le régime séminaire eulérien, au sens que si on réécrit les solutions en coordonnées autosimilaires, donc voilà, avec les vitesses d'explosion mu n qui est ici quelque part, alors les solutions sont proches des solutions autosimilaires de l'équation de l'air, autrement dit, solutions stationnaires de ce truc-là qui était décrite par le théorème juste avant. Et en particulier, les normes L infini pour les deux, pour les vitesses et pour la densité, tend vers l'infini quand on approche le temps d'explosion. Donc les deux explosent. Donc c'est une explosion forte par rapport à l'explosion, par rapport à la singularisation du type de choc. Et ce résultat, en fait, elle est uniforme par rapport à la viscosité. Donc elle est valable aussi bien pour Navier-Stokes que pour LR. Dans le régime de paramètres qu'on regarde. Maintenant, donc, on a le même résultat pour NLS. Donc là, pour NLS, là, je vais venir un peu en arrière parce qu'à un moment donné, voilà. Donc si on compare les conditions de compatibilité, que ce epsilon qui apparaît dans le Schrödinger soit positive, avec les conditions qu'on a mises sur les paramètres, ça sort nécessairement les dimensions plus grandes que 5. D'accord? Donc c'est pour ça, c'est les couples en fait. Les couples sont là, ils correspondent tous à la dimension supérieure ou égale à 5 qui est entre le 9. Et donc, oh pardon, c'est pas ça. Nous sommes là. Et donc pour ces couples-là, de nouveau, il existe une variété de conventions finies, des données initiales dans U0 dans H infini, radial, telles que les solutions correspondantes explosent en temps fini, en 0, avec les normes à l'infini qui tendent vers l'infini, et puis donc, ces solutions qu'on construit ont tous, ne s'annulent pas, donc on peut les écrire en coordonnées hydrodynamiques. Et si on le fait en coordonnées hydrodynamiques, les solutions sont proches des solutions autosimilaires de l'équation LR, donc, comme avant. Et une autre chose qui est importante, c'est qu'on regarde, si on regarde les normes de Sobolev de ces solutions, donc on sait que si une solution explose, toutes ces normes Sobolev surcritiques tendent vers l'infini, mais en fait pour ces solutions-là, il y a aussi des normes sous-critiques qui tendent vers l'infini. Et en fait, là, ça semble être une particularité ou une caractéristique de l'explosion dans le cas de focalisante, parce qu'il y a un travail récent de Boulou qui montre que, pas vraiment dans les dimensions où on travaille là, mais en dimension 3, et pour P égale 3, que si il y a une explosion, alors nécessairement il y a aussi des normes sous-critiques qui tendent vers l'infini. Et ça, c'est un contraste par rapport à ce qu'on sait sur Schrödinger focalisant à énergie surcritique, pour laquelle on a des régimes. Il y a des régimes connus d'explosion, mais dans ces régimes, tous les normes sous-critiques restent bornées, tandis que tous les normes surcritiques explosent. Donc là, peut-être c'est là qu'il y a vraiment quelque chose propre à l'équation, à l'explosion défocalisante. Et puis, une autre chose que la démonstration du théorème donne une description beaucoup plus précise en fait, des solutions qu'on construit. Et en particulier, ça permet de voir que dès qu'on sort de la zone d'explosion, il y a des limites en fait, pour les solutions, donc il y a des profils limites. Et le comportement qui sont H infini en dehors de l'origine. Et à l'origine, leur comportement est complètement en fait, est décrit par le comportement des solutions autosimilaires. En fait. Pour ce profil limite, le comportement par des zéros est donné par le comportement des solutions autosimilaires à l'infini. Et donc en particulier, donc, ce comportement est lié à la vitesse d'explosion, donc la vitesse c'est Rn. Donc on le voit apparaître partout. Pour Schrödinger, en fait, le fait que le profil limite reflète en fait, les vitesses d'explosion est bien connu dans le cas focalisant. Ce qui est complètement nouveau dans ce cas défocalisant, c'est le caractère très oscillant des profils qui apparaissent. Voilà, cette phase-là, c'est quelque chose en fait, nouveau. Bon, à part le fait que déjà l'explosion. Bien. Qu'est-ce que je fais maintenant? Je vais dire quelques mots, je vais essayer de dire quelques mots sur les démonstrations. Donc, la première chose qu'on fait, donc, on change les coordonnées, on passe aux coordonnées autosimilaires pour les deux équations, Navier-Stokes et Schrödinger, pour se retrouver avec ce système renormalisé qui est là, qu'on a déjà vu en fait. Là, je mets deux ensembles, et qui maintenant, donc, pour montrer le théorème que j'ai lancé, il faut montrer que pour ce système, on a des solutions globales en temps autosimilaire, donc taux 0 défini, donc, qui vit sur l'intervalle de la forme taux 0t plus infini, et qui, sur cet intervalle, reste proche des solutions stationnaires que R en 10p et phi en 10p qu'on a pour LR. Et donc, taux 0, c'est le petit paramètre, en fait, 1 sur taux 0, c'est le petit paramètre du problème. Et donc, ça se fait à deux étapes. La première étape consiste à étudier le système linéarisé. Donc, pour linéariser le système linéarisé, on oublie Schrödinger, on oublie Navier-Stokes, on prend l'équation de l'air qui est ici, et on le linéarise autour de la solution stationnaire avec laquelle on travaille. On trouve le système qui est ici. Et la première chose à faire, donc, qui se fait, c'est de montrer décroissance exponentielle en temps, locale en espace. Locale au sens qu'on le montre un tout petit peu au-delà des cônes de lumière. Donc le cône de lumière est déjà apparu quelque part, mais je ne pense pas que je l'ai commenté. Le cône de lumière, on peut le voir facilement. Si on réécrit ce système comme une équation des ondes pour phi. Donc phi, c'est presque psi, à une normalisation près. Et donc en fait, le système, on peut le réécrire sous la forme de cette équation qui est en fait une équation d'onde. Donc elle c'est l'opérateur qui est là. Et puis donc il y a les coefficients qui sont déterminés qui s'expriment en termes du profil R en 10p et phi en 10p. Ils sont sans importance. Le terme principal, donc le symbole principal est là. Il y a ce D0 qui s'annule exactement en poids P2. Donc c'est pour ça qu'on dit que c'est le cône de lumière. Et donc il faut, la première chose qu'on fait, on montre les décroissances exponentielles pour ce dynamique linéaire dans la région de l'espace qui vont un peu au-delà du cône de lumière. Voilà, je ne peux pas dire exactement comment on le fait. Juste un mot, en fait, on le fait en utilisant la théorie des semi-groupes. Donc, on trouve des espaces, en fait, des Sobolev, donc définis dans un voisinage du cône de lumière, avec les poids appropriés, dans lesquels on arrive à montrer que l'opérateur qui apparaissent dans notre système linéarisé est dissipative et maximale. Oh, pardon, non, là, elle est dissipative maximale à une perturbation de rang fini près. Ce qui donc notre décroissance exponentielle est en fait modulée à un nombre fini de directions. C'est pour ça que dans le théorème, on dit que voilà, on a ce type de comportement pour des données qui forment une variété de codimensions finies. Cette codimension finie, elle vient d'un nombre fini d'instabilité pour le système linéarisé. Et puis, bon, c'est un travail. Et puis le deuxième travail, c'est de convertir cette stabilité linéaire eulérienne en stabilité non linéaire complète pour Schrödinger et pour Navier-Stokes. Bon, ça se fait par les arguments du bootstrap qui font intervenir les arguments du type de Prouwer pour contrôler les directions d'instabilité linéaire. Donc ça, c'est assez classique, mais sauf que donc, des arguments de bootstrap, donc on utilise des normes assez sophistiquées en fait. Voilà, donc c'est aussi une deuxième grande partie du travail. Malheureusement, je pense que je dois m'arrêter là, donc je m'arrête.
Est-ce qu'il y a des questions?
Hello, Professor. I suppose that what is the most difficulty of this method to generalize it to the incompressible Navier-Stokes equation case? Because in this case, we know that maybe the first equation for R does not hold, and this term will lose. But what does this method act for the incompressible Navier-Stokes case?
Probably not too much. It works for compressible. You can't. I don't think that there is anything that survives in the limit. I don't think that you can get something for incompressible Navier-Stokes starting from this.
Est-ce qu'en dehors du critère numérique, qu'il fallait que quelque chose ne s'annule pas pour les paramètres et la dimension différente de 4?
Pardon?
La dimension 4 était exclue du résultat. Il y avait un critère numérique qui expliquait ça, mais est-ce qu'il y a d'autres arguments qui font que la dimension 4 est spéciale?
La dimension 4, tu veux dire pour Schrödinger, en fait, pour Navier-Stokes, elle n'était pas faite, en fait, elle n'est pas exclue. C'est juste que Franck, il voulait, je pense, il ne voulait pas couvrir tout, il s'est mis en dimension 3 parce que c'est la dimension plus physique pour Navier-Stokes. Mais pour Navier-Stokes, en fait, il y a des solutions qu'il faut, autosimilaires, pour faire la dimension 4 aussi. Par contre, c'est la dimension 2 qui ne marche pas pour Navier-Stokes. Et la dimension 4 qui ne marche pas pour Schrödinger non linéaire parce qu'il n'y a pas de compatibilité entre les solutions C infinies qu'ils ont construites et en fait le fait que le régime soit, en fait, il faut que le régime de l'R soit dominant. Mais ça ne veut pas dire que voilà, qu'il n'y a pas d'explosion.
On peut remercier encore Galina pour cet exposé.